Hello there, and welcome to Science for Sleep, where curiosity is allowed to slow down, stretch out, and settle comfortably into the quiet hours of the night. This is a place where science is not hurried, where questions are allowed to breathe, and where the universe can be explored without needing to arrive anywhere in a rush. Whether you are listening with eyes half closed, lights dimmed, or simply letting the words drift past you while the day finally loosens its grip, you are very welcome here. Tonight, we are turning our attention outward, far beyond the familiar shapes of our own sky, toward a galaxy that has been watched, mapped, and admired for centuries. A galaxy that feels almost neighbourly by cosmic standards, close enough to be seen with the naked eye on a dark night, yet distant enough to remind us how vast everything truly is. And this time, we are not looking at it with ordinary instruments or even the powerful telescopes of the recent past. We are looking with the James Webb Space Telescope, an observatory designed to see what has never been seen so clearly before. When Webb turned its gaze toward Andromeda, astronomers expected beauty, detail, and confirmation of ideas built carefully over decades. What they did not expect was the quiet sense that something did not quite line up. This is not a story about alarms or sudden danger. Nothing is rushing toward us, and no cosmic disaster is unfolding as we speak. Instead, this is a story about subtle mismatches, gentle contradictions, and the kind of scientific discomfort that comes when reality refuses to behave exactly as predicted. The kind of discomfort that does not shout, but whispers. The kind that makes researchers lean back in their chairs, reread data, and ask themselves whether they're seeing something new, or simply seeing something they thought they already understood, but from a different angle. Before we ease into that story, take a moment to notice where you are right now. What time is it in your part of the world? Is the sky outside dark or just beginning to lighten? Are you listening alone, or is there someone else nearby, perhaps already asleep? These small details matter, not to the science itself, but to how it feels to take it in. After all, astronomy has always been shaped by the human habit of looking up during quiet moments, wondering what is out there while the rest of the world grows still. If you find this kind of slow exploration soothing, or if it helps you unwind after a long day, consider giving the video a like or subscribing to the channel. It helps this calm corner of science reach others who might need it too. There is no rush to do so now. Even that can wait until later. For the moment, all that matters is that you are here, listening, and letting your thoughts drift outward. Now, imagine standing somewhere far from city lights, where the night sky stretches wide and uninterrupted. Above you, faint but unmistakable, is a soft, elongated glow. It does not twinkle like the stars around it. It does not flash or shimmer. It simply sits there, calm and steady, as it has for as long as humans have been able to notice it. That glow is the Andromeda galaxy, a vast collection of stars, dust, gas, and dark matter, bound together by gravity and moving through space on a slow, inevitable path toward our own Milky Way. For generations, Andromeda has been a familiar mystery. Early astronomers debated whether it was a cloud within our galaxy or something far beyond it. When it was finally understood to be a galaxy in its own right, containing hundreds of billions of stars, it reshaped our understanding of the universe overnight. The Milky Way was no longer the whole story. It was one example among many. Since then, Andromeda has been studied in almost every way available. Visible light images revealed its graceful spiral arms. Radio observations traced cold hydrogen gas drifting through its disk. Infrared surveys hinted at regions of star formation hidden behind dust. By the time the James Webb Space Telescope was launched, Andromeda was not considered mysterious in the dramatic sense. It was complex, certainly, and still full of unanswered questions, but its broad structure seemed well understood. Webb was expected to refine details, sharpen measurements, and perhaps fill in gaps at smaller scales. It was not expected to unsettle the bigger picture. James Webb itself represents a very different way of seeing. Unlike telescopes that focus primarily on visible light, Webb is designed to observe the universe in infrared. This allows it to peer through dust that would otherwise block our view and to detect cooler objects that do not glow brightly in visible wavelengths. In practical terms, this means Webb can reveal stars still wrapped in their birth clouds, trace the distribution of warm dust with remarkable clarity, and detect subtle temperature differences across vast regions of space. When astronomers aim Webb at a target, they are not simply taking a prettier picture. They are collecting data that speaks to physical conditions, chemical composition, and history. Light in this context is not just light. It is information that has travelled for millions of years, carrying clues about where it came from and what it passed through along the way. So when Webb began returning its observations of Andromeda, there was a sense of anticipation, but also confidence. This was familiar territory, a well-studied galaxy, now seen with an unprecedented instrument. The expectation was refinement, not revision. At first glance, the images were everything one might hope for. Spiral arms appeared with extraordinary clarity, threaded with filaments of dust glowing softly in infrared light. Star-forming regions stood out as warm knots embedded within cooler surroundings. The sheer level of detail was mesmerizing, even to scientists accustomed to working with data rather than pictures. But as the initial admiration settled into careful analysis, patterns began to emerge that did not sit comfortably with existing models. Some regions appeared warmer than expected, without an obvious source of heating. Other areas that should have been rich in star formation activity seemed oddly subdued. The distribution of dust did not always align with the structures traced by stars and gas in previous observations. These were not dramatic anomalies, not glaring errors that could be dismissed immediately. They were subtle inconsistencies, the kind that only become noticeable when expectations are precise and data is sharp. In science, such moments are both exciting and unsettling. On the one hand, they offer the possibility of learning something genuinely new. On the other, they raise the uncomfortable question of whether long-held assumptions might be incomplete or even wrong. And because Andromeda is so often used as a reference point, a nearby example against which more distant galaxies are compared, any uncertainty about its structure or history has wider implications. It is worth remembering that galaxies are not static objects. They are dynamic systems shaped by gravity, motion, and time. Over billions of years, they grow by forming stars, consuming gas and interacting with their surroundings. They collide with smaller galaxies, absorb them, and are themselves distorted by these encounters. The scars of such events can persist long after the actual collision is over, written into the motions of stars and the distribution of dust and gas. For Andromeda, there is already evidence of a turbulent past. Streams of stars arc through its halo, remnants of smaller galaxies pulled apart by gravity. Its disk shows signs of warping and asymmetry. None of this is new. What is new is the way Webb's observations seem to highlight these features in unexpected ways, and perhaps reveal others that had gone unnoticed. As researchers began comparing Webb's data with observations from other telescopes, questions multiplied. Were these temperature variations real or artifacts of calibration? Did the dust structures indicate previously unseen processes at work, or simply a different perspective on familiar ones? Could the apparent mismatches be explained by known physics applied in more complex ways, or did they hint at something missing from current models? These are not questions that yield quick answers. They require careful cross-checking, additional observations, and above all, patience. The kind of patience that mirrors the slow pace of the universe itself. Galaxies evolve over timescales far longer than any human lifetime. Understanding them demands a willingness to sit with uncertainty, to allow ideas to be revised gradually rather than overturned overnight. There is also a quieter, more human aspect to this process. Scientists, despite the rigor of their methods, are still people. They form mental pictures of how systems work. They develop intuitions shaped by years of study. When new data challenges those intuitions, the reaction is not panic, but curiosity mixed with caution, a careful re-examination of assumptions, a renewed attention to details that might once have seemed settled. Andromeda, in this sense, becomes more than a galaxy. It becomes a reminder that familiarity does not guarantee full understanding, that even our nearest cosmic neighbours can still surprise us, especially when we learn to see them in new ways. As you listen, you might notice your own thoughts beginning to slow, perhaps drifting between the vastness of space and the quiet of your immediate surroundings. This contrast is part of what makes astronomy so uniquely calming. It places everyday concerns against a backdrop of immense scale, not to diminish them, but to give them context. The universe is large and old, yet here you are, present in this moment, able to contemplate it. In the moments ahead, we will gently follow the thread of these unexpected observations. We will talk about what scientists expected to see when Webb looked at Andromeda, and why those expectations made sense at the time. We will explore what the telescope actually revealed, and how those revelations fit, or fail to fit, into existing ideas about how galaxies form and evolve. Along the way, we will touch on dust, stars, heat, and the slow gravitational dances that shape galaxies over billions of years. There is no need to hold on to every detail. This is not a test, and there will be no sudden conclusions demanded of you. Think of it instead as a guided stroll through a quiet observatory, lights dimmed, screens glowing softly, while the night outside remains still. You can listen closely, or let the words fade into the background, knowing they will continue at an unhurried pace. And as we shift from this gentle welcome into the deeper story of Andromeda and the James Webb Space Telescope, keep in mind that what makes this moment interesting is not that something was loudly wrong, but that something was subtly off. A small deviation, noticed only because our tools have become so precise. A reminder that the universe still has room to surprise us, even in places we thought we knew well. When people talk about nearby places in the universe, the word nearby does a lot of work. Space has a way of stretching our intuition until familiar words lose their everyday meaning, and yet, among the countless galaxies scattered across the observable universe, there is one that truly earns the title of neighbour. Not close in the sense of walking distance, or even planetary distance, but close enough that it has shaped how we understand galaxies at all. That galaxy is Andromeda. If you were to step outside on a clear dark night far from city lights, Andromeda would already be there, whether you noticed it or not. It appears as a faint elongated smudge in the sky, just bright enough to be seen without any optical aid if conditions are right. For most of human history, it was simply part of the background, an odd patch of light that did not behave like a star. It did not twinkle. It didn't shift its position noticeably from night to night. It was steady, quiet, and easy to overlook unless you knew to look for it. Long before telescopes, ancient observers recorded Andromeda as a cloud or a mist among the stars. The Persian astronomer Abd al-Rahman al-Sufi described it in the 10th century as a little cloud, a remarkably accurate description given the tools available at the time. For centuries after that, it remained exactly that in the human imagination. A curiosity, but not a revelation. Even when telescopes became more common, Andromeda's true nature was slow to emerge. Early instruments could resolve stars in our own Milky Way, but Andromeda resisted such clarity. It appeared larger, brighter, and more structured than a typical nebula, but still unresolved. This ambiguity placed it at the centre of one of astronomy's most important debates. Was Andromeda a nearby cloud of gas within our own galaxy, or was it something far larger and farther away? That question was not settled until the early 20th century. When astronomers like Edwin Hubble began identifying individual stars within Andromeda, particularly Cepheid variable stars whose brightness could be used to measure distance, the implications were immediate and profound. Andromeda was not part of the Milky Way at all. It was a galaxy in its own right, containing hundreds of billions of stars, located far beyond the boundaries of our own stellar system. This realization fundamentally changed humanity's place in the universe. The Milky Way was no longer the entire cosmos. It was one galaxy among many, and Andromeda was its nearest large companion. Suddenly, the universe expanded dramatically in both size and complexity. Today, we know that Andromeda lies about 2.5 million light-years away. That means the light reaching your eyes tonight began its journey long before modern humans existed. It left Andromeda when early hominins were just beginning to use simple stone tools. In cosmic terms, this is practically next door. Most galaxies we study are tens, hundreds, or even billions of light-years away. Andromeda's relative closeness makes it an invaluable reference point. In size, Andromeda rivals or slightly exceeds the Milky Way. It is a massive spiral galaxy with a broad disk, sweeping spiral arms, a dense central bulge, and an extended halo of stars and dark matter. Estimates suggest it may contain around 1 trillion stars, though the exact number depends on how faint a star one chooses to count. That uncertainty itself is a reminder of how difficult it is to measure even our closest galactic neighbours. Because Andromeda is both large and close, it has been observed across nearly the entire electromagnetic spectrum. Visible light images reveal its classic spiral shape. Radio observations trace cold hydrogen gas extending far beyond the visible disk. Ultraviolet surveys highlight regions of recent star formation. X-ray telescopes detect energetic phenomena like supernova remnants and accreting compact objects. Each wavelength tells a different part of the story. Over time, these observations have been woven together into a coherent picture of Andromeda as a mature spiral galaxy with an active past. It has formed stars steadily over billions of years, though not at an especially frantic pace. It has interacted with and absorbed smaller satellite galaxies, leaving behind streams of stars that still drift through its outskirts. It has a supermassive black hole at its centre, quiet compared to those in more active galaxies, but still influential. One of the reasons Andromeda feels so important is that it offers an external view of something we can never see directly from within the Milky Way. Because we are embedded inside our own galaxy's disk, our perspective is limited. Dust obscures large portions of the Milky Way, and our position makes it difficult to map its overall structure with precision. Andromeda, by contrast, is laid out before us almost in full. We can see its spiral arms, its bulge, its halo, all from the outside. For decades, astronomers have used Andromeda as a comparison point. If we want to understand what a large spiral galaxy looks like from afar, Andromeda is the template. Models of galactic structure, star formation, and evolution are often tested against what we observe there. When something behaves differently in a distant galaxy, Andromeda serves as a baseline for what normal might look like. This is why unexpected observations of Andromeda matter so much. If something does not make sense there, it raises questions not only about that galaxy, but about how well our models apply more broadly. Another reason Andromeda holds a special place in astronomy is its relationship with the Milky Way. These two galaxies are not static islands drifting aimlessly through space. They are gravitationally bound to each other, locked in a slow dance that will eventually end in a merger. Measurements of Andromeda's motion show that it is moving toward us, not away. In about 4 billion years, the two galaxies are expected to collide and eventually merge into a single, larger galaxy. This future encounter is often described dramatically, but in reality it will be a slow, drawn-out process. Stars are so far apart that direct collisions between them are extremely unlikely. Instead, gravitational forces will reshape both galaxies, distorting their disks, triggering bursts of star formation, and redistributing stars into new orbits. Over time, the combined system may settle into a more elliptical shape. While this merger lies far in the future, understanding Andromeda's current structure and history helps astronomers model how that eventual union might unfold. Subtle features in Andromeda today, such as warps in its disk or asymmetries in its stellar populations, may be the result of past interactions that offer clues about what lies ahead. Andromeda is not alone in its neighbourhood. It is surrounded by dozens of smaller satellite galaxies, some of which are being gradually torn apart by tidal forces. These satellites form a loose system, similar to the collection of dwarf galaxies that orbit the Milky Way. Studying these systems provides insight into how large galaxies grow over time by accreting smaller ones. The halo of Andromeda, an extended region of stars and dark matter surrounding the main disk, is particularly rich in information. It contains stellar streams that trace the paths of past mergers, like faint scars left behind by long-forgotten encounters. These streams can be mapped in detail because of Andromeda's proximity, allowing astronomers to reconstruct parts of its history with surprising precision. Despite all this accumulated knowledge, Andromeda has always retained an element of mystery. Some of its features are difficult to explain cleanly. Its disk shows signs of heating and disturbance that suggest significant interactions in the past. Its star formation history appears uneven, with periods of enhanced activity that may correspond to mergers or close encounters. Its central bulge is unusually large and complex compared to that of the Milky Way. None of these puzzles are new, but they have traditionally been addressed with data that, while impressive, still left a room for interpretation. Infrared observations before James Webb, for example, were limited by resolution and sensitivity. They could detect dust and warm regions, but not with the clarity needed to disentangle fine structures across the galaxy. This is where Webb changes the situation. By observing Andromeda in infrared wavelengths with unprecedented detail, Webb allows astronomers to see through dust clouds that obscure visible light. It reveals the distribution of warm dust heated by stars, traces star-forming regions at earlier stages, and provides temperature maps that hint at underlying processes. Because Andromeda is so close, Webb's resolution translates into physical detail on scales that are difficult or impossible to achieve for more distant galaxies. Features that would blur together elsewhere can be resolved into distinct structures. This sharpness is both a gift and a challenge. The clearer the picture becomes, the harder it is to ignore discrepancies. There is also a psychological element to studying a familiar object with a new instrument. Expectations are deeply ingrained. Astronomers approach Andromeda with a mental model shaped by decades of observation and theory. When Webb's data deviates from that model, the deviation stands out more starkly than it might for a galaxy studied for the first time. In that sense, Andromeda's familiarity works against complacency. It forces careful scrutiny. If something seems off, it cannot be dismissed easily as ignorance. It demands explanation. The phrase, "nearest great neighbour in the dark," captures this duality well. Andromeda is near enough to feel known, yet distant enough to remain fundamentally other. It shines faintly in our sky, a reminder that even the darkness is full of structure and history. It has been there for all of recorded human history, quietly orbiting alongside us, its light crossing intergalactic space to reach our eyes. As we prepare to look more closely at what James Webb has revealed, it helps to hold this broader context in mind. Andromeda is not just a random target. It is a cornerstone of galactic astronomy, a reference point, a benchmark, and a future collision partner. Any surprise there resonates widely. The questions raised by Webb's observations do not imply that everything we thought we knew about Andromeda is wrong. Science rarely works that way. Instead, they suggest that the picture may be incomplete, that additional layers of complexity remain to be uncovered. Perhaps processes that play a minor role elsewhere are more prominent here. Perhaps the timing and impact of past interactions were different than assumed. Perhaps our models of how dust, gas, and stars interact need refinement. These are quiet questions, not sensational ones. They do not demand immediate answers. They invite careful thought and further observation. Andromeda has waited billions of years to be understood. It can wait a little longer. As your thoughts continue to drift through this immense but gentle landscape, it may help to remember that astronomy progresses in this way, not through constant upheaval, but through gradual adjustments, guided by better data and sharper tools. The James Webb Space Telescope is one such tool, and its gaze toward Andromeda is only beginning to be fully explored. Long before the first images ever arrived, long before mirrors unfolded in space or detectors cooled to their operating temperatures, the James Webb Space Telescope existed as an idea shaped by limitations, not by what astronomers wanted to see, but by what they could not. For decades, telescopes had been pushing against the boundaries of visible light, refining clarity, sharpening focus, and extending reach. Yet again and again, the same obstacles appeared. Dust obscured key regions. Cold objects remained faint. The earliest chapters of cosmic history stayed just out of reach, hidden behind the expansion of the universe itself. Webb was conceived to address those blind spots, not by improving what had already been done, but by looking in a fundamentally different way. Its purpose was never to replace earlier observatories, but to complement them by opening a window that had remained only partially transparent. To understand why its observations of Andromeda feel so revealing, it helps to understand precisely what Webb was designed to notice, and just as importantly, what it was designed to ignore. Unlike telescopes that focus primarily on visible light, Webb operates almost entirely in the infrared. This choice was not arbitrary. Infrared light occupies a region of the electromagnetic spectrum just beyond what human eyes can detect. It is associated with heat, with cooler objects, and with radiation that stretches as it travels across expanding space. Many of the most important structures in the universe emit most of their information in these wavelengths, not because they are dramatic or energetic, but because they are cold, dusty, or deeply embedded within their surroundings. Star formation offers a clear example. Stars are born inside dense clouds of gas and dust. In visible light, these regions often appear as dark silhouettes, blocking the light of stars behind them. The dust grains scatter and absorb shorter wavelengths, making the interiors of these clouds effectively invisible. Infrared light, however, passes through dust far more easily. A telescope sensitive to infrared can peer inside these clouds and observe stars while they are still forming, wrapped in the material that will eventually disperse. This ability to see through dust is central to Webb's mission. It allows astronomers to study processes that were previously inferred indirectly. Instead of guessing where stars might be forming based on surrounding activity, Webb can observe the process more directly. It can detect the warm glow of dust heated by newly formed stars, trace the structure of star-forming regions, and map how gas and dust are distributed on fine scales. Infrared sensitivity also makes Webb exceptionally good at detecting cooler objects. Many astronomical phenomena do not emit strongly in visible light. Brown dwarfs, objects too small to sustain hydrogen fusion like true stars, glow primarily in infrared. Protoplanetary disks, the flattened structures of gas and dust around young stars where planets form, are best studied at longer wavelengths. Even mature planets emit most of their radiation as heat, rather than visible light. Beyond individual objects, infrared observations are essential for studying the distant universe. As the universe expands, light travelling across vast distances is stretched, shifting toward longer wavelengths. Light that was originally emitted in visible or ultraviolet ranges arrives at Earth as infrared. To observe the first galaxies and stars, formed not long after the Big Bang, a telescope must be sensitive to infrared radiation. Webb was built with this in mind, allowing it to look farther back in time than any previous observatory. But Webb's design is not just about wavelength. Its sheer size plays a critical role. The telescope's primary mirror spans over 6 meters in diameter, significantly larger than that of the Hubble Space Telescope. A larger mirror collects more light, increasing sensitivity and resolution. This means Webb can detect fainter objects and resolve finer details, especially when combined with infrared detectors optimized for low noise performance. The mirror itself is segmented, composed of 18 hexagonal pieces that work together as a single reflective surface. This design was driven by practical constraints. A mirror of that size could not fit inside any existing rocket fairing as a single piece. Segmenting the mirror allowed it to be folded for launch and deployed once in space. Each segment is coated with a thin layer of gold, chosen for its excellent reflectivity and infrared wavelengths. Once deployed, the mirror segments are adjusted with extraordinary precision. Tiny actuators move each segment to align them to within fractions of the width of a human hair. This alignment process is critical. Any misalignment would blur images and degrade the telescope's performance. The fact that Webb achieved this alignment successfully is a testament to decades of engineering development and testing. Webb's detectors are another key component of its design. They are built to be extremely sensitive to faint infrared signals, but such sensitivity comes with challenges. Infrared detectors are susceptible to noise generated by their own heat. To minimize this, Webb operates at extremely low temperatures. A large, multi-layered sunshield blocks heat from the sun, Earth and Moon, allowing the telescope to cool passively to around 40 kelvins. Some instruments are cooled even further using active cryogenic systems. This emphasis on thermal control is not just an engineering detail, it directly affects what Webb can see. At higher temperatures, the telescope itself would glow in infrared, overwhelming the faint signals from distant objects. By cooling the instruments, Webb reduces this background noise, allowing subtle features to stand out. The telescope's location also matters. Webb orbits the Sun near a point known as the second Lagrange point, or L2, located about 1.5 million kilometers from Earth. At this location, the gravitational influences of the Earth and Sun balance in a way that allows the telescope to maintain a stable position relative to both. This stability simplifies thermal management and allows the sunshield to remain oriented consistently, keeping the telescope in permanent shadow. From L2, Webb has a clear view of the universe, without Earth frequently blocking its line of sight. It can observe targets continuously for long periods, an advantage when collecting detailed data. This uninterrupted view is particularly important for studying faint or complex structures that require long exposure times. Webb carries multiple scientific instruments, each designed to extract different kinds of information from infrared light. Some focus on imaging, producing detailed pictures across various infrared bands. Others perform spectroscopy, splitting light into its component wavelengths to reveal chemical composition, temperature, motion, and other physical properties. Spectroscopy is especially powerful because it turns light into a diagnostic tool. By analyzing specific features in a spectrum, astronomers can identify molecules, measure velocities, and infer physical conditions. When Webb observes a galaxy like Andromeda, it does not simply capture a single image. It collects a rich data set that includes spatial structure and spectral information. This allows scientists to map how properties like temperature, dust composition, and star formation vary across the galaxy. It transforms a familiar object into a complex landscape of physical processes. It is important to emphasize that Webb was not built with Andromeda as its primary target. Its mission priorities include studying the early universe, star and planet formation, and the atmospheres of exoplanets. Observations of nearby galaxies serve both as scientific studies in their own right and as calibration points. Nearby galaxies allow astronomers to test Webb's capabilities and refine their understanding of how to interpret its data. Because Andromeda is close and well studied, it provides a useful benchmark. If Webb's observations match expectations there, confidence increases when interpreting data from more distant, less understood systems. If they do not, it signals that something important may be missing from current models. Webb sensitivity means it often reveals structures that were previously blended together. regions once thought uniform may resolve into complex networks of filaments, knots, and gradients. Temperature variations that averaged out in lower resolution data become apparent. Dust that appeared smoothly distributed may show clumping and layering. This increase in detail is not always comfortable. Simpler models are easier to work with. They allow broad conclusions and straightforward comparisons. When data becomes more detailed, it often exposes complexity that resists easy explanation. Webb does not simplify the universe, it complicates it. There is also a subtle shift in perspective that Webb introduces. Earlier infrared observatories, such as the Spitzer Space Telescope, provided valuable data but with limited resolution. Webb's sharpness bridges the gap between broad surveys and fine-scale studies. It allows astronomers to connect large-scale galactic structures with small-scale physical processes. This connection is crucial for understanding how galaxies function as integrated systems. In the case of Andromeda, this means Webb can examine how spiral arms, dust lanes, and star-forming regions interact. It can trace how energy from stars heats surrounding dust, and how that dust, in turn, influences further star formation. It can reveal whether certain regions are dominated by older stellar populations or by more recent activity. Another aspect of Webb's design that matters is its dynamic range. It can observe both bright and faint features within the same field of view without saturating detectors or losing subtle signals. This capability is particularly useful for galaxies, where bright star-forming regions sit alongside faint diffuse emission. Capturing both simultaneously provides a more complete picture. Webb's observations are also highly quantitative. They are not just visually striking, though they often are. They provide measurements that can be compared directly with theoretical predictions. When a region appears warmer than expected, that temperature can be estimated. When dust emission does not align with stellar distributions, the discrepancy can be quantified. This precision turns aesthetic surprise into scientific tension. It is worth noting that Webb does not see everything. Its instruments are optimized for specific wavelength ranges. It does not observe radio waves or X-rays. It does not replace telescopes designed for those regimes. Instead, it adds a crucial layer of information. Understanding Andromeda fully requires combining Webb's data with observations from many other facilities. This multi-wavelength approach is standard in modern astronomy, but Webb's contribution shifts the balance. It fills in gaps that were previously bridged with assumptions. Where once astronomers inferred the presence of warm dust or embedded star formation, Webb can often observe it directly. Because of this, Webb sometimes confirms expectations with satisfying clarity. In other cases, it complicates them. When patterns do not align, the cause may lie in physics that was oversimplified or in processes that were underestimated. These mismatches are not failures. They are opportunities to refine understanding. The design philosophy behind Webb embraces this possibility. It was built not only to answer existing questions, but to reveal questions that had not yet been asked. Its unprecedented sensitivity and resolution mean it is almost guaranteed to show something unexpected, especially when pointed at complex systems. Andromeda, despite its familiarity, is such a system. It contains layers of history written into its structure, star formation that waxed and waned, mergers that stirred its disk, interactions that left subtle imprints. Webb's ability to isolate different components allows these layers to be examined more distinctly. As observations accumulate, scientists are still learning how to interpret what Webb shows. Calibration continues. Data reduction techniques evolve. Comparisons with simulations are ongoing. This process takes time. It requires careful analysis rather than quick conclusions. For a listener, especially in a quiet moment like this, it can be helpful to think of Webb not as a single eye but as a translator. It converts infrared light, invisible to human senses, into information we can understand. In doing so, it reveals aspects of the universe that were always there, just hidden from view. The sense that something was wrong in Andromeda does not mean Webb discovered an error in the universe. It means it exposed tensions between observation and expectation. Those tensions arise precisely because Webb was built to see what others could not. There is a particular kind of moment in astronomy that carries more weight than it appears to at first glance. It is not the announcement of a discovery, nor the release of a dramatic image, but the quiet decision to point a powerful new instrument at something already well known. On the surface, it can seem almost anticlimactic. Why spend precious observing time on a galaxy that has been studied for generations, when the universe is full of distant, unexplored targets? And yet, this choice is often where the most revealing insights begin. When plans were made to observe Andromeda with the James Webb Space Telescope, the motivation was not spectacle. It was calibration, comparison, and careful curiosity. Andromeda was familiar territory, a benchmark against which Webb's performance could be tested and its data interpreted. Astronomers knew Andromeda's broad features well enough to have expectations, and that made it the ideal place to look for confirmation that Webb was seeing the universe correctly. What followed was a reminder that familiarity does not guarantee predictability. Pointing Webb toward Andromeda was not a single action, but a sequence of carefully planned decisions. The telescope's observing schedule is tightly managed, with each target selected based on scientific priority, instrument availability, and orbital constraints. Andromeda, large and extended across the sky, required particular care. Unlike distant galaxies that fit neatly within a small field of view, Andromeda spans several degrees, far larger than Webb's instruments can capture in one frame. This meant astronomers had to choose specific regions to observe. Spiral arms, dust lanes, star-forming regions, and portions of the central bulge were selected based on prior knowledge. These areas were already mapped by other telescopes, which provided a roadmap of where interesting activity was likely to be found. Webb would not see Andromeda all at once, but in carefully chosen pieces, each offering a different perspective. The decision of where to look carried implicit assumptions. Spiral arms were expected to show clear signs of star formation. Dust lanes were expected to glow softly in infrared, tracing the interstellar medium. The central regions were expected to reveal older stellar populations and complex structures shaped by long-term gravitational dynamics. These expectations were not guesses. They were grounded in decades of observation across multiple wavelengths. In a sense, Webb was being asked to fill in details rather than rewrite the story. Its role was to sharpen, not overturn. That mindset shaped how the observations were approached and how the early data was examined. From an operational standpoint, observing Andromeda also served a practical purpose. Because its properties were relatively well understood, discrepancies between Webb's data and existing models could be used to refine instrument calibration. If Webb measured a temperature or brightness that differed from previous observations, astronomers could investigate whether the difference reflected a real physical feature or an instrumental effect. This process is essential for a new telescope, especially one operating in wavelength ranges where precision is critical. As Webb collected its first infrared views of Andromeda, the data flowed not as images but as streams of numbers. Raw detector readings were processed through complex pipelines that corrected for instrumental effects, background noise, and cosmic interference. Only after this careful processing did recognizable structures begin to emerge. This stage is often invisible to the public, but it is where much of the scientific work happens. When the first processed images were assembled, they looked reassuringly familiar. Spiral patterns appeared where expected. Dust lanes traced the same general path seen in previous infrared surveys. Star-forming regions glowed in roughly the right places. At a glance, Andromeda looked like Andromeda. This initial sense of confirmation was important. It suggested that Webb was performing as designed and that its data could be trusted. But astronomy rarely stops at a glance. As researchers began to analyze the data in detail, subtle differences became harder to ignore. Regions that should have shared similar properties did not always match. Temperature maps showed variations that did not align cleanly with known stellar populations. Dust emission appeared more structured and uneven than models predicted. One reason these differences stood out was precisely because Andromeda was so familiar. If Webb had been observing a distant, poorly understood galaxy, such variations might have been attributed to unknown history or unique conditions. In Andromeda, where expectations were clearer, deviations carried more weight. Another factor was Webb's resolution. Features that had previously blended together were now separated. What once looked like a smooth band of emission could be resolved into distinct filaments and clumps. This raised a fundamental question. Were these structures always there, hidden by limited resolution, or did they represent processes that had been underestimated? Turning Webb's eye toward Andromeda also involved turning scientific attention inward, toward the assumptions embedded in existing models. Many models of galactic structure rely on simplifying averages. They describe how gas, dust, and stars behave on large scales, smoothing over local variations. This approach works well when data is coarse. When data becomes sharper, those averages begin to break down. In the spiral arms of Andromeda, for example, star formation was expected to follow certain patterns. Gas density increases, stars form, radiation heats surrounding dust, and the cycle continues. Webb's observations showed evidence of this process, but not always in the tidy sequence model suggested. Some regions appeared warm without obvious sources of recent star formation. Others showed signs of past activity without corresponding current heating. These mismatches did not suggest that existing theories were wrong, but that they might be incomplete. Additional factors, such as the influence of older stellar populations, variations in dust composition, or the lingering effects of past interactions, could play a larger role than previously thought. The act of observing Andromeda with Webb also highlighted the importance of context. Webb sees infrared light, but that light must be interpreted alongside data from other wavelengths. When Webb revealed a warm region, astronomers compared it with ultraviolet data tracing young stars, radio data mapping gas, and visible light images showing stellar distributions. In many cases, the story made sense. In others, it became more complicated. This complexity is not a flaw. It reflects the reality that galaxies are layered systems where multiple processes operate simultaneously. Webb's contribution is to add resolution and sensitivity to that picture, even when it complicates interpretation. There was also a temporal dimension to these observations. Webb captures a snapshot, a moment frozen in time, but galaxies evolve. The structures Webb sees are the result of processes unfolding over millions or billions of years. A region that appears quiet now may have been active recently, leaving behind heated dust or altered gas distributions. Conversely, a region bustling with star formation may not yet have had time to heat its surroundings significantly. Understanding these time delays requires models that track not just where stars form, but how their energy propagates through the interstellar medium. Webb's data provides constraints on these models, forcing them to account for observed mismatches. The familiarity of Andromeda also made it easier to notice asymmetries. One side of the galaxy did not always mirror the other. Spiral arms differed subtly in structure and activity. Dust distribution varied in ways that suggested uneven history. These features hinted at past disturbances, perhaps from interactions with smaller galaxies that had long since been absorbed. Such interactions are known to shape galaxies, but Webb's observations suggested that their effects might persist more subtly and more unevenly than expected. Rather than dramatic scars, they may leave behind gentle imbalances that only become apparent with sensitive instruments. As scientists continued to examine the data, discussions grew more nuanced. Instead of asking whether something was wrong, the focus shifted to understanding what was different. Language matters in science. A sense of wrongness often signals a gap between expectation and observation, not an error in the data. In Andromeda's case, that gap invited closer inspection. There was also an awareness that Webb's observations represented only a fraction of what could be done. The regions selected for initial study were chosen based on practical constraints and scientific priorities. Many parts of Andromeda remain to be observed in similar detail. Patterns seen in one area may or may not extend across the entire galaxy. This uncertainty encouraged caution. Scientists resisted drawing broad conclusions too quickly. Instead, they treated the early observations as prompts for further investigation. Proposals were drafted for additional observing time. Models were adjusted and tested. Comparisons were made with simulations designed to replicate Andromeda's history. From a broader perspective, turning Webb's eye toward Andromeda served as a rehearsal for interpreting data from more distant galaxies. If Webb revealed unexpected complexity in a nearby system, it suggested that distant galaxies, seen with less contextual information, might harbour even more hidden structure. Andromeda became a training ground for Webb's science, highlighting both its power and the care required to use it well. There is something quietly humbling about this process. Even with a telescope of extraordinary capability, understanding does not arrive fully formed. It emerges slowly through careful comparison, discussion, and revision. Webb does not provide answers in isolation. It provides evidence that must be woven into an existing tapestry of knowledge. As you listen, it may be useful to imagine astronomers poring over these data late at night, screens glowing softly much like this moment. There is no rush in that work either. Patterns are traced, notes are made, questions are raised and left open. The sense that something did not quite line up becomes a thread worth following, not a problem to be fixed immediately. Turning Webb's eye toward a familiar galaxy was never about confirming what was already known. It was about seeing how much more there was to notice when the light was viewed differently. Andromeda, steady and unassuming in the night sky, revealed itself once again as a system rich in detail, layered with history, and subtly resistant to simple description. Before the James Webb Space Telescope ever collected a single photon from Andromeda, there already existed a well-established mental picture of what should appear. This picture was not speculative or vague. It was built carefully over decades, assembled from observations made by dozens of telescopes operating across different wavelengths, combined with theoretical models refined through years of comparison and revision. When scientists pointed Webb toward Andromeda, they were not venturing into the unknown. They were revisiting familiar ground with sharper eyes. Expectations in science are not guesses. They are structured predictions. They arise from patterns that have held up repeatedly, from physical laws that have proven reliable, and from models that, while simplified, have successfully explained a wide range of observations. In the case of Andromeda, those expectations were particularly strong, because it is one of the most studied galaxies in existence. At the larger scale, astronomers expected Andromeda to look like a textbook spiral galaxy in infrared light. Its spiral arms were already mapped in visible, ultraviolet, and radio wavelengths. Infrared observations from earlier missions such as Spitzer and Herschel had traced the broad distribution of dust and star-forming regions. Webb was expected to refine this view, sharpening edges, resolving finer structure, and filling in details where previous data blurred together. In the spiral arms, scientists expected to see clear signatures of ongoing and recent star formation. These regions are where gas clouds are compressed by density waves, triggering the collapse of material into new stars. Young, massive stars emit intense radiation that heats surrounding dust, causing it to glow in infrared wavelengths. This glow should trace the arms in a relatively predictable way, aligned with gas density and stellar activity. The interarm regions, by contrast, were expected to appear quieter. Less gas, fewer young stars, cooler dust. Not empty, certainly, but subdued compared to the bright structured arms. Any infrared emission there was expected to come primarily from older stars gently heating diffuse dust, rather than from active star-forming complexes. The central region of Andromeda carried its own set of expectations. The galaxy's core is dominated by older stars, with relatively little ongoing star formation compared to more active galaxies. Infrared observations were expected to show warm dust heated by this older stellar population, along with complex structures shaped by long-term gravitational dynamics. The supermassive black hole at the centre, while present, is relatively quiet, so it was not expected to dominate the infrared emission. Beyond the main disk, the halo of Andromeda was expected to be faint in infrared. This extended region contains stars stripped from smaller galaxies over billions of years, along with dark matter. Infrared emission there was expected to be minimal, with only weak signals from sparse dust or isolated sources. At a more detailed level, scientists had expectations about temperature distributions. Dust temperature is a key diagnostic in infrared astronomy. Warmer dust typically indicates proximity to young energetic stars. Cooler dust suggests either distance from heating sources or shielding within dense clouds. Models predicted relatively smooth temperature gradients across the galaxy, modulated by spiral structure and local star formation. Chemical composition also played a role in expectations. Different types of dust grains emit infrared radiation differently. Prior observations suggested a fairly consistent dust composition across Andromeda's disk, with variations tied to star formation history and metallicity. Webb's instruments, capable of distinguishing subtle spectral features, were expected to confirm these patterns with greater precision. Another expectation concerned symmetry. While no galaxy is perfectly symmetric, Andromeda was thought to be relatively well behaved in this regard. Its two main spiral arms appeared broadly similar in structure and activity. Any asymmetries were expected to be minor, reflecting gradual evolution rather than dramatic disturbance. These expectations were reinforced by simulations of spiral galaxies similar to Andromeda. Computational models incorporate gravity, gas dynamics, star formation, and feedback from stars and supernovae. When tuned to match Andromeda's known properties, these models reproduced many observed features reasonably well. Discrepancies existed, of course, but they were generally understood as limitations of resolution or simplifying assumptions. Because Webb offered higher resolution and sensitivity, scientists anticipated that it would reveal complexity within this overall framework, not contradict it. The hope was to see the same structures more clearly, to measure properties more precisely, and to identify smaller-scale features that fit naturally into the existing picture. There was also an expectation that Webb would help resolve long-standing questions about Andromeda's star formation history. Previous studies suggested that Andromeda experienced periods of enhanced star formation in the past, possibly triggered by mergers with smaller galaxies. Infrared data from Webb was expected to help distinguish between older and younger stellar populations by tracing dust heating and residual star formation activity. In particular, astronomers were interested in whether Andromeda's disk showed signs of recent rejuvenation. Some models suggested that interactions with satellite galaxies could have stirred gas and reignited star formation in certain regions. Webb's sensitivity to warm dust and embedded stars made it an ideal tool to test these ideas. Another expectation involved dust distribution. Dust lanes in Andromeda had been mapped in visible light as dark streaks and in infrared as broad emission regions. Webb was expected to reveal these lanes in exquisite detail, showing how dust is organized on smaller scales and how it interacts with surrounding gas and stars. The underlying assumption was that this organization would follow known physical processes, such as turbulence, gravity, and stellar feedback. Importantly, scientists did not expect Webb to reveal fundamentally new types of structures in Andromeda. New details, yes. New physics, probably not. Andromeda was not thought to host extreme environments like those found in starburst galaxies or active galactic nuclei. It was considered a relatively mature, stable system. These expectations shaped how the observations were planned. Instrument settings, exposure times, and target regions were chosen based on predicted brightness and structure. Observations were optimized to capture known features with maximum clarity. There was little reason to anticipate surprises so subtle that they would challenge established interpretations. This confidence was not arrogance. It was the natural result of cumulative knowledge. When a model works across many systems and wavelengths, it earns trust. Andromeda had repeatedly validated key aspects of galactic theory. Webb was expected to extend that validation into new territory, yet expectations also create a framework that can make deviations more noticeable. When something does not align, it stands out sharply against the predicted background. In Andromeda's case, Webb's observations did not shatter the existing picture, but they introduced small tensions that were difficult to ignore precisely because the expectations were so clear. Some regions appeared warmer than predicted without corresponding signs of recent star formation. This challenged the assumption that young stars are always the dominant heating source for dust. Other regions showed dust structures that did not align with gas density or stellar distribution in straightforward ways. These mismatches were not dramatic enough to invalidate models, but they suggested missing ingredients. Even symmetry, long assumed to be a reasonable approximation, appeared more nuanced. Webb's data hinted at subtle differences between spiral arms that could not be explained solely by viewing angle or minor variations. This raised questions about whether past interactions had left more uneven imprints than previously thought. It is important to emphasize that these deviations emerged gradually. There was no single image or dataset that announced something was wrong. Instead, patterns accumulated. As different teams analyzed different regions and compared notes, a shared sense emerged that Webb was highlighting complexity that existing models smoothed over. This is often how progress occurs in astronomy. Expectations are not overturned in dramatic fashion. They are stretched, adjusted, and refined. Each new observation adds texture to the picture, revealing where simplifications break down. The expectation that Andromeda would behave predictably was, in many ways, fulfilled. The galaxy did look like a spiral galaxy. Its overall structure matched previous observations. But Webb's view suggested that predictability operates within bounds. Beyond those bounds, local history, subtle interactions, and internal processes introduce variation that models must account for. As you listen, it may help to think of expectations as a map rather than a destination. They guide exploration, but they are not the territory itself. Webb's observations did not invalidate the map of Andromeda, but they revealed contours and features that had been smoothed out or overlooked. When the first processed images from the James Webb Space Telescope began to circulate among the team studying Andromeda, the immediate reaction was quiet admiration. There was no dramatic announcement, no sudden declaration that something extraordinary had been found. Instead, there was a moment of stillness, the kind that follows when expectations are met visually, even exceeded, but not yet questioned. The galaxy appeared with a clarity that was unmistakably new. Familiar shapes were there, but rendered with a precision that invited closer inspection. At a distance, the images felt reassuring. Andromeda's broad spiral form was intact, its arms sweeping outward in graceful arcs. The central region glowed softly, dense with stars whose combined light warmed surrounding material. Dust lanes traced winding paths through the disk, no longer vague or blended, but sharply defined. There was a sense that Webb had delivered exactly what it promised, a clearer, deeper look at a galaxy long admired. Infrared light has a way of transforming familiar scenes. Features that dominate visible light images recede, while others come forward. In Webb's images, the bright glare of individual stars gave way to the softer glow of dust and gas. Regions that once appeared dark and opaque became translucent, revealing structures hidden beneath layers of interstellar material. It was not a different galaxy, but a different expression of the same one. The detail was immediately striking. Dust was no longer a smooth backdrop, but a complex network of filaments, knots, and wisps. These structures followed spiral patterns in some places, but in others they curved, split, or thickened in ways that suggested local influences. The arms themselves appeared layered, with subtle variations in brightness and texture that hinted at different physical conditions along their length. Star-forming regions stood out as clusters of warm emission embedded within cooler surroundings. These regions were not uniform. Some appeared compact and intense, while others were diffuse and extended. The variation was expected to some degree, but the scale of it drew attention. Webb was not simply showing where stars were forming, but how uneven and localized that process could be. As scientists moved beyond initial impressions and began to examine specific regions, the images started to feel less straightforward. The beauty remained, but it was accompanied by a growing sense that the details did not always align neatly with established expectations. The unsettling quality did not come from any single anomaly, but from patterns that resisted simple explanation. One of the first things to stand out was the distribution of infrared brightness across the disk. In broad terms, the spiral arms were brighter than the regions between them, as expected. But within those arms, brightness varied in ways that did not always correspond to known star clusters or gas concentrations. Some areas glowed warmly without obvious nearby sources of young energetic stars. Temperature maps derived from the infrared data added to this impression. Dust temperature is inferred by comparing emission at different wavelengths. Warmer dust emits more strongly at shorter infrared wavelengths, while cooler dust dominates longer wavelengths. When these measurements were applied across Andromeda, the resulting patterns were more complex than anticipated. In some regions, dust temperatures were higher than models predicted, even though visible and ultraviolet data showed little evidence of recent star formation. In others, areas with known young stellar populations did not exhibit the level of heating expected. These discrepancies were subtle, often within margins that could be attributed to local variation, but they appeared consistently enough to merit attention. Another unsettling aspect emerged from the structure of the dust itself. Earlier infrared observations had suggested that dust in Andromeda was distributed relatively smoothly along spiral arms, with gradual transitions into interarm regions. Webb's images revealed a more fragmented picture. Dust appeared clumped on smaller scales, forming networks that did not always follow the larger spiral pattern cleanly. These clumps and filaments suggested that local processes played a significant role in shaping the interstellar medium. Turbulence, magnetic fields, and feedback from stars all influence how dust and gas behave, but the relative importance of these factors is still an active area of research. Webb's images implied that such processes might be more influential or more uneven than models had assumed. Attention also turned to the central regions of Andromeda. The galaxy's core had been studied extensively, and its general properties were well known. Webb's infrared view revealed a dense concentration of warm dust and stars as expected, but also highlighted asymmetries that were not immediately obvious in previous data. The distribution of emission was not perfectly centered or uniform. These asymmetries raised questions about the history of the central region. Was the distribution shaped by past interactions, by bar-like structures that channel material inward, or by variations in the stellar population over time? Webb did not answer these questions directly, but it made them harder to ignore. In the outer disk, where emission was fainter, Webb's sensitivity brought new features into view. Subtle arcs and patches of dust appeared where little had been detected before. Some of these features aligned with known stellar streams, remnants of smaller galaxies that Andromeda had absorbed. Others did not have obvious counterparts in existing maps. The presence of dust in these regions was itself intriguing. Dust is produced by stars and distributed through the interstellar medium by winds and supernovae. Finding it in the outskirts of the galaxy suggested efficient transport mechanisms or past events that had redistributed material more widely than expected. As the images were examined in greater detail, comparisons with older datasets became essential. Teams overlaid Webb's infrared maps with optical images, ultraviolet surveys, and radio observations of gas. In many cases, features aligned as expected. In others, the correspondence was imperfect. These mismatches were not errors in the data. Webb's calibration had been carefully checked. The instrument was performing as designed. The discrepancies reflected real differences in what different wavelengths revealed. Infrared light traced warm dust, optical light traced stars, radio waves traced gas. The fact that these traces did not always line up neatly pointed to complexity in how these components interact. One particularly interesting pattern involved regions where dust emission appeared strong, but gas density, as measured by radio observations, was relatively low. This challenged simple assumptions about the relationship between gas and dust. While they are generally well correlated, local conditions can alter that balance. Webb's data suggested that such conditions might be more common in Andromeda than previously recognized. The unsettling quality of the images was amplified by their consistency. If only one region showed unexpected behavior, it might be dismissed as an outlier. Instead, similar patterns appeared in multiple locations. The same types of discrepancies repeated, hinting at underlying processes rather than random variation. At the same time, it was clear that Webb was not contradicting everything known about Andromeda. The overall structure remained intact. The spiral arms were still spiral arms. The galaxy was still forming stars at a modest rate. There was no dramatic revision of its identity. The discomfort lay in the details, in the sense that the finer the view became, the less tidy the picture looked. This tension is familiar in scientific progress. Increased resolution often reveals complexity that was previously averaged out. When models are built on coarse data, they naturally emphasize dominant trends. When those trends are examined at finer scales, deviations emerge. The challenge is to determine which deviations are significant and which are simply the expected result of looking more closely. For Andromeda, Webb's images pushed that challenge into sharper focus. The galaxy had long been considered a relatively calm system, especially compared to more active or disturbed galaxies. Webb's view suggested that calmness might be more apparent than real, a result of smoothing over subtle but widespread variation. There was also an emotional dimension to this moment. Astronomers are trained to be cautious, to resist over-interpreting early data, yet they are also human, and the act of seeing a familiar object in a new way can be surprisingly affecting. The images were undeniably beautiful, but beauty in science often accompanies deeper questions. The phrase, slightly unsettling, captures this blend of responses. There was no sense of alarm, no implication that something had gone wrong with the telescope or the theory. Instead, there was a growing awareness that the story of Andromeda was more textured than previously thought. As discussions unfolded, researchers began to ask new questions. Could older stars contribute more to dust heating than models accounted for? Could the composition of dust vary enough to alter emission patterns significantly? Had past interactions left lingering effects that were only now becoming visible? These questions did not demand immediate answers. They pointed toward future work, toward refining models and planning additional observations. Webb's images served as a starting point rather than a conclusion. For someone listening quietly, perhaps late at night, there is something fitting about this stage of the story. The universe reveals itself not through sudden revelations, but through gradual shifts in understanding. A familiar galaxy becomes slightly unfamiliar, not because it has changed, but because we have learned to see it differently. As the initial sense of admiration gave way to closer examination, a subtle shift occurred in how Andromeda was being discussed. The language did not become dramatic or alarmist. No one suggested that the galaxy was broken, or that established physics had failed. Instead, conversations began to include phrases that carried a different weight. Words like unexpected, inconsistent, harder to reconcile. These were not expressions of confusion, but of careful attention. They signaled that Andromeda, when viewed through Webb's instruments, was not behaving exactly as the models had led scientists to expect. In astronomy, behaviour does not mean motion in the everyday sense. Galaxies do not make sudden decisions or change course abruptly. Their behaviour is inferred from patterns, distributions and relationships between physical components. When those relationships do not line up as predicted, it suggests that something in the underlying assumptions needs revisiting. One of the first areas where this became apparent was in how energy seemed to move through Andromeda's disk. In simplified terms, energy in a galaxy flows outward from stars. Young, massive stars emit large amounts of radiation, which heats surrounding gas and dust. That heated material then glows in infrared wavelengths. This process is well understood and forms the basis for interpreting infrared observations. In Andromeda, Webb's data showed this process clearly in many places. Bright star-forming regions were associated with warm dust, and the overall structure made sense. But interspersed among these expected patterns were regions where the relationship broke down. Dust appeared warmer than it should have been given the apparent lack of nearby young stars. In other areas, known stellar populations did not produce the level of heating models predicted. These deviations were not isolated. They appeared in multiple spiral arms and at various distances from the galactic centre. Each instance, taken alone, might have been dismissed as a local peculiarity. Taken together, they suggested that the mechanisms governing dust heating were more complex than the dominant models accounted for. One possibility was that older stars were contributing more to dust heating than previously assumed. In many models, the influence of older, cooler stars is treated as a background effect, secondary to the intense radiation from young stars. Webb's observations hinted that this background might be more significant, especially in a galaxy like Andromeda, with a large population of mature stars. Another possibility involved the composition and structure of the dust itself. Dust is not uniform. It consists of grains of different sizes, shapes, and chemical compositions. These properties affect how dust absorbs and emits radiation. If Andromeda's dust differs in subtle ways from the assumptions built into models, its infrared emission could behave differently. Webb's ability to resolve fine structure brought this issue into sharper focus. Dust lanes that once appeared smooth now resolved into intricate networks. Within these networks, conditions could vary on small scales, affecting how energy is absorbed and re-radiated. Models that averaged over larger regions might miss these variations entirely. Beyond dust heating, gas dynamics also appeared less straightforward than expected. Radio observations had mapped the distribution of cold gas in Andromeda, showing where star formation was likely to occur. Webb's infrared data, however, sometimes highlighted warm regions where gas density appeared lower. This challenged the assumption that gas concentration and infrared emission would always correlate closely. Such discrepancies raised questions about timing. Star formation is not instantaneous. A region that recently formed stars might retain warm dust even after the most massive stars have evolved or moved on. Conversely, gas-rich regions might be on the verge of star formation, but not yet show strong infrared signatures. Webb snapshots captured moments in this ongoing process, and interpreting them required careful consideration of temporal effects. The galaxy's spiral arms provided another arena, where behaviour diverged from prediction. Traditional models describe spiral arms as relatively coherent structures where star formation follows predictable sequences. Webb's data show that while this description holds in broad terms, the details are messier. Star-forming regions did not always line up neatly along the arms. Some appeared offset, others scattered in patterns that suggested local influences. This irregularity could reflect the dynamic nature of spiral arms themselves. Rather than being rigid structures, spiral arms are density waves that move through the disk, compressing gas as they pass. The interaction between these waves and the interstellar medium can be complex, especially in a galaxy with Andromeda's history. Webb's observations suggested that this complexity plays out on smaller scales than previously appreciated. Attention also turned to asymmetries across the galaxy. While Andromeda's overall shape is symmetric enough to be classified as a spiral, Webb's detailed view revealed imbalances. One arm might show more extensive warm dust than its counterpart. Certain regions on one side of the galaxy behaved differently than similar regions on the other. These asymmetries hinted at past events that had left uneven imprints. Andromeda is known to have absorbed smaller galaxies over its lifetime. Such interactions can distort gas flows, trigger star formation, and redistribute material. While the most dramatic effects fade over time, subtle differences can persist. Webb's sensitivity made these lingering effects more visible. The central regions of Andromeda offered another example of unexpected behavior. The core is dominated by older stars, and its infrared emission was expected to be relatively uniform. Instead, Webb revealed patchiness and structure that suggested a more active or varied history. Warm dust appeared in places where models predicted cooler conditions. This raised questions about the role of internal processes. Bars, rings, and other structures can channel gas toward the center of a galaxy, fueling intermittent activity. Even if such activity occurred long ago, it could leave behind signatures in dust distribution and temperature. Webb's observations suggested that the central region's history might be more complex than a simple, steady evolution. One of the more intriguing aspects of this behavioral mismatch was how subtle it was. There were no glaring contradictions, no single observation that forced an immediate rewrite of theory. Instead, the discomfort came from accumulation. Each small deviation added weight to the idea that something was missing from the current picture. This is a familiar experience in science, though it is rarely discussed outside specialist circles. Models are not expected to be perfect. They are tools that capture dominant trends. When data becomes more detailed, the limitations of those tools become apparent. The question then becomes whether the deviations point toward refinements or toward more fundamental changes. In Andromeda's case, most scientists lean toward refinement. The core principles of galactic evolution remained sound. Gravity still governed motion. Star formation still followed known physical laws. Feedback from stars still shaped the interstellar medium. What Webb highlighted was the need to incorporate additional layers of realism. These layers include variations in dust properties, more nuanced treatments of stellar populations, and better accounting for the lingering effects of past interactions. Incorporating such factors into models is challenging. It increases computational complexity and demands more detailed input data. Webb's observations provided motivation to undertake that effort. Another aspect of Andromeda's behavior that drew attention was the relationship between structure and history. Galaxies are shaped by their past, but that past is not always obvious in present-day appearances. Webb's data suggested that Andromeda's history might be written more clearly into its small-scale structure than previously thought. Stellar streams in the halo are an obvious example. These remnants of past mergers are visible because they consist of stars that have not yet fully mixed into the galaxy. Webb's infrared view hinted that similar remnants might exist within the disk itself, embedded in dust and gas rather than stars alone. If true, this would complicate the interpretation of Andromeda's disk. Features once attributed solely to internal processes might instead reflect the aftermath of external events. Distinguishing between these possibilities requires careful modelling, and in some cases additional observations. The sense that Andromeda was not behaving as predicted did not produce anxiety among scientists. It produced focus. Workshops, discussions, and collaborative analyses emerged, aimed at understanding the discrepancies. Webb's data became a shared reference point, a set of observations that everyone agreed were high quality and worthy of attention. This collective effort underscored an important aspect of astronomical research. Discoveries rarely emerge fully formed from a single dataset. They are built through dialogue, comparison, and gradual consensus. Webb's observations of Andromeda initiated such a process. For someone listening quietly, there is something reassuring about this pace. The universe does not demand immediate interpretation. It allows room for uncertainty, for questions to remain open while understanding develops. Andromeda's unexpected behaviour did not disrupt the calm of the night sky. It deepened it, adding texture to something already familiar. It is also worth noting that the phrase "didn't behave as predicted" carries a gentle humility. It acknowledges that predictions are human constructs, approximations of reality. When reality diverges from them, it is not a failure of nature, but an opportunity to learn. As Webb continues to observe Andromeda and other galaxies, this pattern is likely to repeat. Familiar systems will reveal unfamiliar details, models will be tested and adjusted. The overall picture will become richer, even if it becomes less tidy. Once attention shifted from broad impressions to specific details, the discussion around Andromeda became more precise. The sense that the galaxy was behaving a little differently than expected began to crystallize around three recurring themes. Certain regions appeared dimmer than they should have been. Other regions were warmer than models predicted. And underlying both of these was a growing awareness of patterns that did not line up cleanly with long-standing assumptions. None of this suggested chaos. It suggested quiet inconsistency, the kind that only emerges when observations are detailed enough to expose the seams in our understanding. The idea of missing light may sound dramatic, but in practice it is subtle. Astronomers do not expect galaxies to shine uniformly. Variations in brightness are normal and well understood. What drew attention in Webb's data were areas where infrared emission was noticeably weaker than predicted, given what was known about the local stellar population and gas content. In regions where star formation had been identified through ultraviolet or optical surveys, infrared emission from warm dust was expected to be strong. Young stars emit large amounts of energy, much of which is absorbed by surrounding dust and re-emitted in infrared wavelengths. This relationship forms the basis for using infrared light as a tracer of star formation. Webb's observations confirm this relationship in many places. Bright knots of infrared emission coincided with known star-forming regions as expected. But there were exceptions. Some regions with evidence of recent star formation appeared surprisingly faint in infrared. The dust there did not glow as warmly or as brightly as models suggested it should. Several explanations were considered. One possibility was that the dust content in these regions was lower than expected. If less dust were present to absorb stellar radiation, less infrared emission would result. However, gas and dust are usually closely linked, and radio observations did not always support a significant deficit of material. Another possibility involved dust properties. Dust grains vary in size and composition, and these factors influence how efficiently they absorb and emit radiation. If the dust in certain regions consisted of grains that radiated less efficiently in Webb's observed wavelengths, the infrared emission could appear weaker without requiring less dust overall. Timing also mattered. Star formation is episodic. A region that formed stars recently may have already lost its most massive, energetic stars, which evolve quickly. The remaining stellar population might not produce enough radiation to heat dust strongly, even though evidence of recent activity remains. Webb's snapshot captured a moment in this ongoing cycle, and interpreting it required considering where each region sat in that timeline. While missing light prompted careful analysis, unexpected heat generated even more discussion. In several areas of Andromeda, dust temperatures inferred from Webb's data were higher than models predicted, without obvious sources of intense radiation nearby. These warm regions did not align neatly with clusters of young stars or with gas concentrations typically associated with heating. This discrepancy challenged a core assumption that young massive stars dominate dust heating. In galaxies like Andromeda, which have large populations of older stars, it had long been assumed that their contribution to dust heating was relatively modest. Webb's data suggested that this assumption might underestimate their role. Older stars emit less energetic radiation, but they are far more numerous. Their combined output can be substantial, especially in regions where young stars are sparse. If this diffuse radiation field is stronger or more spatially complex than models account for, it could heat dust more effectively than expected. Webb's ability to resolve fine structure made this possibility more plausible. Rather than treating stellar populations as smooth distributions, Webb's data revealed gradients and clustering even among older stars. These variations could create localized heating effects that models averaged away. Another potential contributor to unexpected heat was mechanical energy. Stellar winds, supernova remnants, and shocks from past interactions can deposit energy into the interstellar medium. While such processes are often associated with recent star formation, their effects can persist long after the stars that caused them have evolved. Heated dust in regions without obvious young stars could reflect the lingering aftermath of such events. The central regions of Andromeda provided a particularly interesting case. The galaxy's core is dominated by older stars, and its supermassive black hole is relatively quiet. Yet Webb's data showed pockets of warm dust that were difficult to explain solely by the current stellar population. This raised questions about past activity in the core, possibly linked to periods of enhanced accretion or internal restructuring. Beyond missing light and unexpected heat, Webb's images revealed patterns that resisted straightforward interpretation. These patterns were not random. They were coherent structures that appeared repeatedly across different parts of the galaxy. One such pattern involved the alignment or misalignment of dust and gas. In many galaxies, dust emission closely follows gas density because dust is mixed with gas in the interstellar medium. Webb's observations of Andromeda showed areas where this relationship held and others where it did not. Warm dust appeared where gas density was lower, and dense gas regions sometimes showed weaker dust emission. This misalignment suggested that local conditions could decouple dust behavior from gas in ways not fully captured by existing models. Processes such as radiation pressure, magnetic fields, and turbulence can affect dust and gas differently. Webb's data hinted that these processes might play a larger role in shaping Andromeda's interstellar medium than previously recognized. Another pattern involves spiral structure. Spiral arms are often depicted as well-defined features, where gas, dust, and star formation align in a predictable sequence. Webb's detailed view revealed that while this sequence exists on average, it breaks down locally. Star-forming regions were sometimes offset from dust lanes, and dust structures sometimes curved away from the main arm. These offsets could reflect the dynamic nature of spiral arms as density waves rather than fixed structures. Gas enters a spiral arm, is compressed, forms stars, and then moves on. The timing of this process can vary, leading to spatial offsets between different traces. Webb's resolution made these offsets visible in ways that coarser data could not. In addition, Andromeda's spiral arms are not identical. Webb's data suggested subtle differences in structure and behavior between them. One arm might show more fragmented dust or more widespread heating than the other. These differences hinted at asymmetric influences, possibly from past interactions with satellite galaxies. The outer regions of Andromeda also displayed patterns that drew attention. Webb detected faint dust emission farther from the galaxy's center than expected. This dust appeared in arcs and patches that did not correspond neatly to known stellar structures. Its presence raised questions about how dust is transported and retained in the outskirts of large galaxies. Dust can be expelled from the disk by stellar feedback or by tidal interactions. Over time, some of it may fall back, while some may remain suspended in the halo. Webb's observations suggested that such processes might be more effective in Andromeda than models assumed, or that past events had redistributed material in ways still visible today. The phrase, patterns that shouldn't be there, does not imply impossibility. It reflects a mismatch between expectation and observation. The patterns Webb revealed were physically plausible, but they were not anticipated in the form or extent observed. This gap between prediction and reality is where scientific interest concentrates. As teams analysed these features, they compared Webb's data with simulations of galaxy evolution. In some cases, similar patterns appeared in simulations, but only under specific conditions. These conditions often involved complex histories, such as multiple minor mergers or prolonged interactions with satellite galaxies. Andromeda is known to have a rich system of satellites, some of which show signs of past disruption. Webb's observations suggested that the effects of these interactions might extend deeper into the disk than previously thought. Rather than producing obvious, large-scale distortions, they may have subtly reshaped the distribution of dust and gas. Another factor considered was the role of dark matter. While dark matter does not emit light, it shapes the gravitational potential of a galaxy. Variations in this potential can influence gas flows and star formation patterns. If Andromeda's dark matter halo has an irregular structure, perhaps shaped by past mergers, it could contribute to the observed patterns. These considerations did not point to a single explanation. Instead, they suggested that multiple factors were interacting. Dust properties, stellar populations, feedback processes, and galactic history all played roles. Webb's data did not simplify this picture. It complicated it in productive ways. It is important to note that none of these findings implied a crisis. The core principles of astrophysics remained intact. The discrepancies were quantitative and structural, not conceptual. Gravity still governed motion, radiation still transferred energy. The challenge lay in capturing the full complexity of these processes in models. For scientists, this stage of analysis was both demanding and energizing. It required careful separation of signal from interpretation. Each unexpected feature had to be tested against alternative explanations, instrumental effects, and statistical variation. Webb's high-quality data made this possible, but it also raised the bar for confidence. For a listener, especially one easing toward rest, there is something steadying about this process. The universe reveals itself slowly through patterns that require patience to discern. The missing light and unexpected heat are not disruptions, but invitations to look more closely. As understanding deepened, attention began to shift toward the underlying causes of these patterns. Rather than cataloguing anomalies, scientists sought to place them within a broader narrative of Andromeda's past. If the present-day galaxy bore these subtle inconsistencies, they likely reflected events that occurred long ago. This perspective naturally led to questions about time. How long do such patterns persist? How quickly does a galaxy forget its past? As the investigation moved deeper into the details revealed by Webb, attention gradually shifted away from dust and heat alone and toward the stars themselves. Not the bright, short-lived stars that announce their presence loudly through intense radiation, but the quieter majority. The older stars, the ones that have been orbiting Andromeda for billions of years, long enough to be considered part of its stable background. These stars were not expected to surprise anyone, and yet when viewed through the context provided by Webb's infrared observations, some of them began to feel oddly misplaced. To understand why this mattered, it helps to consider how astronomers usually think about stellar populations in a galaxy like Andromeda. Large spiral galaxies are often described as layered systems. Younger stars tend to be found in the thin disk, especially along spiral arms where gas is abundant and star formation is ongoing. Older stars are more broadly distributed. Many reside in the thick disk or the central bulge, while others populate the extended halo, moving on orbits that reflect ancient events. This general picture has served astronomy well. It explains observed distributions of light, motion, and chemical composition across many galaxies. Andromeda, in particular, has been a key example. Its stellar populations had been mapped in detail using visible and near-infrared observations long before Webb. The ages, motions, and metallicities of many of its stars were already reasonably well constrained. What Webb added was context. By mapping dust emission and temperature alongside stellar distributions with unprecedented clarity, it allowed astronomers to see how stars and their environments interacted on fine scales. It was in this interaction that certain stars began to stand out as strangely out of place. In several regions of Andromeda's disk, Webb's data suggested significant dust heating without obvious contributions from young stars. This led researchers to look more closely at the older stellar populations in those areas. When they did, they found concentrations of mature stars whose spatial distribution did not align neatly with expectations based on standard galactic structure models. These stars were not anomalies in age or composition on their own. Individually, they appeared entirely normal. It was their placement, their grouping, and their apparent influence on surrounding material that drew attention. In some cases, older stars seemed to be clustered in regions where models predicted smoother distributions. In others, they appeared to dominate areas that should have been shaped more strongly by recent star formation. One possibility was that these stars were simply more influential than previously thought. Older stars emit less energetic radiation than young stars, but they are numerous. In a galaxy like Andromeda, the cumulative output of billions of mature stars can create a diffuse radiation field capable of heating dust. If that radiation field is uneven due to clustering or structural features, it could produce localized effects that Webb detected. This idea challenged a long-standing simplification. Many models treat the radiation from older stars as a smooth background, contributing gently and uniformly to dust heating. Webb's observations suggested that this background might be more structured, reflecting the galaxy's internal architecture and history. Another explanation involved stellar migration. Over billions of years, stars do not remain fixed in place. Gravitational interactions, spiral density waves, and past mergers can alter stellar orbits. A star born in one region may drift far from its birthplace over time. If Andromeda experienced significant internal rearrangement or external perturbations, its older stars might now occupy unexpected locations. Evidence for such migration already existed. Studies of stellar motions in Andromeda had revealed a dynamically complex system, with stars moving on a wide range of orbits. Webb's observations added a new layer by linking these stars to their surrounding dust environment. In some regions, the presence of older stars appeared correlated with dust structures that did not match the current spiral pattern. This raised the possibility that these stars were remnants of past configurations. They might trace older spiral arms, long since shifted or dissolved. Alternatively, they could belong to stellar streams embedded within the disk, remnants of smaller galaxies that had merged with Andromeda and been stretched into elongated structures. The idea of embedded stellar streams is not new, but it is challenging to confirm. In visible light, such streams can be difficult to distinguish from the background disk. Infrared observations by highlighting dust and temperature variations can provide indirect clues. If stars originating outside the main disk carry different dust environments or influence surrounding material differently, they may stand out in Webb's data. Some of the stars that appeared out of place were located in regions where dust properties differed subtly from their surroundings. The dust there might emit at slightly different wavelengths or show different temperature profiles. This suggested a shared history between the stars and the dust, possibly originating from a disrupted satellite galaxy. Andromeda is known to have absorbed multiple smaller galaxies over its lifetime. The most prominent evidence lies in its halo, where stellar streams arc gracefully through space. But not all mergers leave such obvious signatures. Smaller or older events may deposit stars directly into the disk, where they become harder to distinguish. If Webb's observations were hinting at such embedded remnants, it would imply that Andromeda's disk is more of a mosaic than a uniform structure. Instead of being built solely from stars formed in place, it may include significant contributions from accreted systems, each carrying its own characteristics. Another intriguing aspect involved the vertical distribution of stars. Spiral galaxies have thin disks, where most star formation occurs, and thicker components populated by older stars. Webb's data suggested that some older stars influencing dust heating might reside above or below the main disk plane. Their radiation could illuminate dust layers differently, creating temperature patterns that did not align with the thin disk structure. This vertical complexity is difficult to observe directly, especially in galaxies viewed at an angle like Andromeda. Infrared data can provide indirect evidence by revealing how dust at different heights is heated. Webb's sensitivity made it possible to detect such effects more clearly. There was also the question of metallicity, the abundance of elements heavier than hydrogen and helium. Older stars tend to have lower metallicities, reflecting the composition of the universe at the time they formed. Dust composition is closely tied to metallicity, as dust grains are built from heavier elements produced in stars. If certain regions of Andromeda contained older, lower metallicity stars, the dust there might differ in composition. This could affect its infrared emission, contributing to the patterns Webb observed. Untangling this relationship required careful spectroscopic analysis, comparing stellar properties with dust signatures. What made these findings particularly compelling was their consistency across multiple regions. The impression that some older stars were out of place did not arise from a single anomaly. It emerged from repeated instances where stellar distributions and dust behavior did not align with simple expectations. At the same time, caution was essential. Infrared observations can be influenced by line-of-sight effects. Andromeda's disk is inclined relative to our viewpoint, meaning that stars at different distances along the line of sight can overlap in projection. Apparent associations might not reflect true physical proximity. To address this, researchers combined Webb's data with kinematic information, measuring how stars move within the galaxy. If stars thought to be influencing dust heating shared similar motions, it would strengthen the case that they were physically associated. Early analyses suggested that in some cases this was indeed true. The presence of ancient stars in unexpected places also had implications for Andromeda's star formation history. If these stars originated in different environments, they could indicate periods of intense interaction or restructuring in the galaxy's past. Such events might have reshaped the disk, redistributed material, and left a lasting imprint visible today. This perspective shifted the narrative from one of present-day behavior to one of memory. Galaxies remember their past, not through conscious recollection, but through the distribution of stars, dust, and motion. Webb's observations suggested that Andromeda's memory might be more detailed than previously recognized. It is important to note that none of this implied disorder. The galaxy was not chaotic. Its stars still orbited in coherent patterns. Its disk remained intact. What changed was the level of nuance required to describe it accurately. The simple picture of neatly separated stellar populations gave way to a more interwoven view. For scientists, this was both challenging and satisfying. It meant revisiting assumptions, refining models, and embracing complexity. For a listener, especially one settling into rest, it offered a gentle reminder that even ancient familiar systems can hold surprises when seen clearly. The idea of ancient stars looking out of place carries a quiet poignancy. These stars have existed for billions of years, outliving countless generations of others. They have witnessed Andromeda's transformations, its encounters, its slow evolution. That they now appear slightly misaligned with our expectations says more about those expectations than about the stars themselves. As the analysis continued, these stellar peculiarities became one more thread woven into a larger tapestry. Dust, heat, gas, and stars all contributed to a picture of Andromeda that was richer and more layered than before. None of these elements alone explained the discrepancies. Together they pointed toward a history shaped by subtle interactions and gradual change. By the time attention settled on the interstellar medium itself, the sense that Andromeda was quietly resisting simplification had already taken hold. Dust and gas are often treated as the connective tissue of a galaxy, the material that links stars to one another and carries the imprint of past and present activity. In many models, their behavior is assumed to be reasonably well coupled. Where gas goes, dust follows. Where stars form, both respond in predictable ways. Webb's observations suggested that in Andromeda this coupling was present, but not nearly as tidy as expected. Gas, particularly cold hydrogen gas, has long been mapped in Andromeda using radio telescopes. These maps show large-scale spiral patterns, extended reservoirs in the outer disk, and concentrations where star formation is likely to occur. Dust, on the other hand, is traced most clearly in infrared light, where it glows after absorbing radiation from stars. For decades, comparisons between gas and dust maps painted a broadly consistent picture. The two components overlapped closely enough that discrepancies could often be attributed to resolution limits or observational noise. Webb changed the scale of that comparison. Its infrared sensitivity and resolution allowed dust structures to be mapped, with a sharpness that radio observations even today struggle to match. When astronomers began overlaying Webb's dust maps with existing gas data, the alignment was not as straightforward as anticipated. In many regions, dust and gas still correlated well. Spiral arms rich in hydrogen gas also showed strong dust emission. Star-forming complexes appeared where both components were abundant. This consistency reinforced confidence that Webb's data were tracing real physical structures. But threaded through these confirmations were areas where the relationship faltered. Dust emission sometimes peaked in regions where gas density was lower than expected. Conversely, dense gas clouds occasionally showed weaker dust signatures than models predicted. These were not rare exceptions. They appeared often enough to demand explanation. One possibility involved the physical separation of dust and gas on small scales. While dust and gas are mixed in the interstellar medium, they do not always move together perfectly. Radiation pressure from stars can push dust grains more effectively than gas. Magnetic fields can guide charged dust particles along paths that differ slightly from neutral gas flows. Over time, these effects can create offsets that are invisible at coarse resolution, but become apparent when viewed closely. Webb's images suggested that such decoupling might be widespread in Andromeda. Dust filaments curved and twisted in ways that did not always mirror gas structures. Some dust lanes appeared displaced relative to gas concentrations, hinting at differential motion or past disturbances. The role of turbulence also came under scrutiny. The interstellar medium is not calm. It is stirred by stellar winds, supernova explosions, and large-scale galactic dynamics. Turbulence can fragment gas clouds, compress dust locally, and create complex structures that defy simple alignment. Webb's data revealed a level of fragmentation that suggested turbulence might be more influential, or at least more unevenly distributed than models assumed. In regions affected by past star formation, turbulence can persist long after the most energetic stars have disappeared. Gas motion stirred by ancient supernovae may still shape dust distributions today. This could explain why some dust structures appear energetic or irregular in areas without obvious current star formation. Magnetic fields added another layer of complexity. While difficult to observe directly, magnetic fields influence the behavior of charged particles, including many dust grains. Observations in other galaxies have shown that dust filaments can align with magnetic field lines, creating structures that reflect invisible forces. Webb's detailed dust maps hinted at organized patterns that might be shaped by such fields, though confirming this would require additional data. Another factor was the three-dimensional structure of Andromeda's disk. From our vantage point, we see the galaxy at an angle, not face-on. Dust and gas at different heights above or below the disk plane can overlap in projection, creating apparent misalignments. Webb's sensitivity to faint emission made it possible to detect dust in layers that were previously invisible, complicating the interpretation of two-dimensional maps. In some cases, dust emission appeared to trace material that had been lifted out of the disk, possibly by stellar feedback or tidal interactions. Gas might have fallen back more quickly, or dispersed differently, leaving dust suspended in regions where gas density appeared low. This vertical separation would naturally produce mismatches between dust and gas tracers. The outer disk of Andromeda provided particularly intriguing examples. Webb detected faint dust structures far from the galaxy's centre, beyond regions where significant gas concentrations were expected. These structures formed arcs and patches that did not align neatly with known spiral arms or gas reservoirs. Their presence raised questions about how dust reaches and survives in such environments. Dust grains are fragile on cosmic timescales, subject to destruction by shocks and radiation. Finding them in the outskirts suggested either efficient transport mechanisms or relatively recent redistribution. Tidal interactions offered one possible explanation. As Andromeda interacted with satellite galaxies, gravitational forces could have pulled gas and dust outward, stretching them into extended features. Over time, gas might disperse or cool below detection thresholds, while dust, heated by diffuse radiation, remained visible in infrared. Another possibility involved galactic fountains. In this process, energetic events in the disk push gas and dust upward into the halo, where it cools and eventually rains back down. If dust follows a different trajectory or timescale than gas, temporary misalignments could result. Webb's observations hinted that such circulation might be active in Andromeda. The inner disk showed its own set of challenges. Near the central regions, gas flows can be influenced by bars, rings, or other non-axis symmetric structures. These features can channel material inward or redistribute it unevenly. Webb's dust maps revealed structures that suggested complex flows, with dust tracing paths that did not always coincide with gas inflow models. This raised the possibility that Andromeda's internal dynamics were more intricate than assumed. While the galaxy does not host a prominent bar like some spirals, subtle asymmetries could still influence material transport. Webb's data provided hints of such influences, though interpreting them required careful modelling. Throughout this analysis, an important distinction emerged between what refused to line up and what simply required a new perspective. Many of the mismatches between dust and gas were not contradictions of physical laws. They were signs that the interstellar medium behaves in ways that are sensitive to local conditions, history, and geometry. Models often assume steady-state conditions or average behaviours. Real galaxies, especially ones with long and active histories, may rarely be in such states. Webb's observations of Andromeda suggested that equilibrium, if it exists, is constantly being perturbed by small-scale processes. Another layer of complexity involved chemical evolution. Gas and dust evolve chemically over time, enriched by successive generations of stars. Variations in metallicity across Andromeda could affect dust formation and survival. Regions with different enrichment histories might show different dust-to-gas ratios, altering the apparent alignment between tracers. Spectroscopic data from Webb began to shed light on this possibility. Subtle differences in emission features suggested variations in dust composition across the disk. These variations could contribute to differences in brightness and temperature independent of gas density. As these ideas were explored, the notion that structures refused to line up took on a more nuanced meaning. It was not that the galaxy was disordered, but that it was layered. Each tracer revealed a different aspect of its structure, shaped by overlapping processes operating on different timescales. For scientists, this realization required patience. Untangling these layers meant combining data from multiple wavelengths, constructing three-dimensional models, and testing scenarios against simulations. It was a slow process, iterative rather than decisive. For a listener, especially one settling into quiet reflection, there is something grounding in this approach. The universe does not yield its structure all at once. It reveals it gradually, through careful attention to details that at first seem misaligned. Dust and gas in Andromeda did not behave badly, they behaved richly. Webb's observations invited a shift away from expecting neat correspondence and toward appreciating complexity born of history and motion. As this understanding deepened, it became clear that dust and gas were not merely passive components responding to stars. They were active participants in the galaxy's evolution, carrying memory of past events and shaping future ones. Their refusal to line up neatly was itself a record of Andromeda's long life. Long before Webb ever observed Andromeda, astronomers understood that no large galaxy lives an entirely peaceful life. Gravity does not allow it. Over billions of years, galaxies drift, approach one another, brush past and sometimes collide. Even when these encounters are gentle by cosmic standards, they leave marks. The challenge has always been determining how deeply those marks are written into a galaxy's present-day structure, especially when that galaxy appears calm and orderly at first glance. With Andromeda, the prevailing assumption for many years was that its most dramatic interactions lay far in the past. Yes, it had absorbed smaller companions. Yes, it showed stellar streams in its halo, but its disk, its spiral arms, and its overall form seemed stable, settled, and mature. Whatever disturbances had occurred were thought to be largely smoothed out, their effects diluted by time and rotation. Webb's observations quietly challenged that comfort, not by revealing obvious scars or violent disruptions, but by suggesting that the past might still be influencing Andromeda in ways that are subtle, persistent, and easy to overlook unless one is looking with exceptional clarity. The idea of a disturbed past does not require catastrophe. It does not mean Andromeda was torn apart or radically reshaped. In fact, the most enduring disturbances in galaxies often come from events that are modest in scale but repeated over long periods. A series of minor mergers, a close flyby that perturbs gas, flows without destroying structure. The gradual accretion of satellites that dissolve quietly into the disk rather than announcing their arrival. These kinds of events do not always leave dramatic visual evidence. Instead, they alter trajectories, redistribute material, and change the internal balance of a galaxy. Over time, those changes can manifest as asymmetries, mismatches, and irregularities that only become obvious when examined in detail. One of the reasons this possibility gained traction was the sheer consistency of Webb's subtle anomalies. Missing infrared emission here, unexpected warmth there, dust structures that curved away from gas, older stars appearing to influence regions where they were not expected to dominate. None of these features demanded a violent explanation on their own. Together they hinted at a history shaped by more than simple, isolated evolution. Astronomers have long known that Andromeda possesses a rich halo of stellar debris. Large streams of stars arc around the galaxy, remnants of dwarf galaxies that ventured too close and were pulled apart by tidal forces. These streams are clear evidence of past interactions, and they are relatively easy to identify because they stand out against the sparse halo background. What is more difficult to detect are the remnants of interactions that deposit material directly into the disk. When a smaller galaxy merges on a trajectory aligned with the disk plane, its stars and gas can become thoroughly mixed. Over time, they cease to look like an external addition and instead become part of the disk's fabric. The only clues to their origin may lie in subtle differences in motion, composition, or spatial distribution. Webb's observations suggested that such mixing may have played a larger role in Andromeda than previously appreciated. Dust and stars that seemed slightly out of place could be the quiet signatures of these embedded mergers. Their presence would not disrupt the spiral arms outright, but it could introduce irregularities that persist for billions of years. Another aspect pointing toward a disturbed past was the unevenness observed across Andromeda's disk. Spiral galaxies are often assumed to be roughly symmetric on large scales, especially if they have not experienced recent major interactions. Webb's data suggested that Andromeda's symmetry breaks down more readily at smaller scales. One spiral arm might exhibit more fragmented dust, or warmer average temperatures than its counterpart. Certain regions on one side of the galaxy behave differently than similar regions on the opposite side. These differences were not random. They appeared structured and repeatable, suggesting underlying causes rather than observational noise. Asymmetry is a classic indicator of past interaction. Even a minor encounter can tug unevenly on a galaxy, altering gas flows and triggering star formation in some regions while suppressing it in others. Over time, these effects can propagate, creating long-lived imbalances that are subtle but measurable. There was also growing interest in the timing of such disturbances. Webb's observations provided clues not just about what might have happened, but about when. The temperature of dust, the distribution of older stars, and the absence of strong current star formation in certain warm regions all suggested that some of the heating sources were no longer active. This pointed toward events that occurred hundreds of millions or even billions of years ago. Not recent enough to leave bright clusters of young stars, but not ancient enough to be completely erased by galactic rotation and mixing. Simulations of galaxy evolution support this idea. When a spiral galaxy experiences a minor merger, the immediate effects can fade relatively quickly. Star formation triggered by the interaction may last tens or hundreds of millions of years. Gas flows may settle over similar timescales. But the redistribution of stars and dust can persist far longer, especially if the merger deposits material at different radii or heights within the disk. Webb's ability to detect fine-scale structure made it sensitive to these lingering effects. Where earlier observations averaged over large regions, Webb could isolate pockets of material that retained a memory of past disturbances. The central regions of Andromeda added another layer to this narrative. The galaxy's core had long been considered relatively quiet, dominated by old stars and lacking the intense activity seen in some galactic centers. Webb's infrared data, however, revealed complexity that suggested a more dynamic past. Warm dust in the core, patchy rather than uniform, hinted that energy had been deposited unevenly. This could reflect past inflows of gas, possibly driven by interactions or internal instabilities. Even if such inflows ceased long ago, their effects on dust distribution could persist. There was also the possibility that Andromeda once hosted a more active central environment. Many galaxies undergo phases where their central black holes accrete more material, releasing energy that affects surrounding gas and dust. Even a modest episode of such activity could leave traces detectable in infrared emission long after the black hole quieted down. While there was no evidence of dramatic past activity on the scale of quasars or powerful active galactic nuclei, Webb's observations did not rule out smaller, more transient events. In fact, the subtlety of the observed features made such scenarios more plausible. The outskirts of Andromeda offered additional hints. Dust detected far from the main disk suggested that material had been displaced from its original location. This displacement could occur through tidal interactions, where gravitational forces stretch and pull material outward. It could also result from internal processes, such as galactic fountains driven by star formation. In either case, the presence of dust in these regions implied movement and redistribution. Gas and dust do not migrate so far without cause. The fact that these features appeared structured rather than diffuse supported the idea of specific past events rather than gradual uniform evolution. Another line of reasoning came from comparing Andromeda to similar galaxies. When Webb and other telescopes observe spiral galaxies beyond the local group, they often reveal signs of disturbance, even in systems that appear orderly at first glance. Warped disks, lopsided gas distributions, and uneven star formation are common. Andromeda's apparent calm may have been partly a matter of perspective and resolution. Viewed with less sensitive instruments, its irregularities blended into a smooth whole. Webb's view suggested that Andromeda is not unusually disturbed, but rather more typical than previously thought. This realization carries important implications. If even our nearest large neighbour retains subtle imprints of past interactions, then the notion of truly isolated, undisturbed spiral galaxies becomes less tenable. Galactic evolution may be shaped more consistently by interaction than by isolation. It is important to emphasize that disturbance does not imply instability. Andromeda is not falling apart. Its disk remains coherent. Its stars follow predictable orbits on average. What disturbance implies is complexity layered atop stability. This distinction matters because it reframes how astronomers interpret irregularities. Instead of treating them as anomalies to be smoothed away, they become data points that encode history. Dust that does not line up. Heat that appears without obvious cause. Stars that seem out of place. All of these can be understood as echoes of events that occurred long ago. From this perspective, Webb's observations do not contradict previous understanding. They enrich it. They add depth to a narrative that was once flatter, filling in intermediate chapters between dramatic mergers and long-term equilibrium. There is also a methodological lesson here. Galaxies are often studied by separating processes into categories: internal versus external, secular evolution versus interaction-driven change. In reality, these categories blur. A minor interaction can trigger internal instabilities. Internal processes can amplify the effects of external perturbations. Over time, the distinction becomes less clear. Webb's data made this blurring visible. Features that might once have been attributed solely to internal dynamics could now plausibly be linked to past interactions. Conversely, some irregularities might arise from internal processes acting over long timescales without any external trigger. This ambiguity is not a weakness. It reflects the richness of galactic systems. Understanding them requires moving beyond simple either-or explanations and embracing overlapping influences. For scientists, the possibility of a disturbed past in Andromeda prompted renewed interest in reconstructing its interaction history. Simulations were revisited with updated constraints. The timing and mass of past mergers were reconsidered. Observational campaigns aimed at mapping stellar motions and chemical abundances gained new relevance. For a listener, especially one easing into rest, there is something quietly compelling about this idea. The notion that a galaxy can look calm while carrying the memory of countless encounters mirrors experiences closer to home. History does not always announce itself loudly. Sometimes it is written into small imbalances and subtle patterns. Andromeda's light has travelled millions of years to reach us. What Webb revealed is not a moment of upheaval, but a long accumulation of experience. A galaxy shaped gently but persistently by its environment. Long before Andromeda appeared as a graceful spiral smudge in human skies, long before its stars settled into the patterns we now recognise, it existed within a crowded and restless environment. Galaxies do not form in isolation. They emerge within groups, surrounded by smaller companions, embedded in webs of dark matter that guide motion and interaction. Over cosmic time, these surroundings leave an imprint. Some encounters are obvious, dramatic and easy to trace. Others fade quietly, leaving behind only subtle clues that require careful observation to uncover. When Webb's observations raised the possibility of a disturbed past, they did not point toward a single catastrophic collision. Instead, they hinted at a history shaped by repeated encounters, mergers with smaller systems and interactions that were significant enough to matter, but not violent enough to destroy structure. These are the kinds of events that create what astronomers often refer to, informally, as ghost galaxies. Ghost galaxies are not literal apparitions. They are the remnants of systems that once existed independently, complete with their own stars, gas, dust, and dark matter, but which have since been absorbed into a larger host. Their identity dissolves over time, but not completely. Traces remain, stretched into streams, shells, ripples, or embedded populations that no longer resemble their original form. Andromeda is already known to be rich in such remnants. Long before Webb, astronomers had identified vast stellar streams looping around the galaxy, especially in its halo. These streams are the shredded remains of dwarf galaxies that ventured too close and were torn apart by tidal forces. Their stars now follow elongated paths, tracing the gravitational contours of Andromeda's dark matter halo. One of the most prominent of these is the giant stellar stream, a massive arc of stars extending tens of thousands of light-years from Andromeda's core. Its existence alone confirms that Andromeda has experienced at least one substantial merger in the relatively recent cosmic past, perhaps within the last few billion years. That event was significant enough to leave a clear, visible structure that has not yet been fully erased by orbital mixing. But not all mergers announce themselves so clearly. Smaller galaxies, or those that merged earlier, can leave behind subtler signatures. Their stars may disperse more completely, blending into the disk or halo. Their gas may fuel star formation and then dissipate. Their dust may mix unevenly with existing material. Over time, the only clues may lie in chemical fingerprints, orbital patterns, or localized structural irregularities. Webb's observations suggested that Andromeda may harbor many such ghosts, not just in its halo, but within its disk itself. The misplaced older stars, the dust structures that refuse to align, and the uneven heating patterns all pointed toward a history where material from outside systems had been incorporated into the galaxy in ways that models had smoothed over. Collisions in the astronomical sense are rarely head-on impacts. More often they are slow, drawn-out interactions. A small galaxy approaches, its stars beginning to feel the gravitational pull of the larger system long before physical contact. Tidal forces stretch it, strip material away and gradually dissolve it. This process can take hundreds of millions of years, sometimes longer. During this time, the larger galaxy is not a passive recipient. Its disk can be disturbed. Gas flows can be altered. Spiral patterns can be amplified or weakened. Star formation can be triggered in some regions and suppressed in others. Even after the smaller galaxy is fully absorbed, the effects can persist. One of the challenges in identifying these long-forgotten encounters is that their signatures overlap with internal processes. Spiral arms themselves can redistribute stars. Bars can drive gas inward. Turbulence can fragment dust. Disentangling what came from outside versus what arose internally is difficult, especially when relying on limited resolution data. Webb's contribution was not to solve this problem outright, but to sharpen it. By revealing fine-scale structure, it made it possible to see inconsistencies that were previously hidden, regions where dust composition differed subtly, areas where older stars clustered unexpectedly, temperature patterns that suggested energy input long after obvious triggers had faded. These features are exactly what simulations predict for galaxies that have experienced multiple minor mergers. Each event leaves a small imprint. Individually, they may be insignificant. Collectively, they create a galaxy that looks calm overall but contains layered complexity. Another clue lay in the apparent timing implied by Webb's observations. Many of the anomalies did not correspond to ongoing star formation. Instead, they appeared to reflect processes that had occurred in the past and whose energetic signatures were lingering. This is consistent with merger-driven activity that has since subsided. Simulations of Andromeda's evolution already suggest that it may have undergone a relatively massive merger several billion years ago, possibly with a galaxy comparable in size to the Large Magellanic Cloud. Such an event would not destroy Andromeda's disk entirely, but it could thicken it, redistribute stars, and create asymmetries that persist for a long time. If this merger occurred early enough, its most dramatic effects would have faded. Starbursts would have ended, gas would have settled. What remained would be structural memory, written into the distribution of stars and dust. Webb's sensitivity made it possible to detect such memory in the infrared, where dust and older stellar populations dominate. Beyond mergers, close flybys also matter. A galaxy does not need to collide to be disturbed. Passing nearby can be enough. Gravitational tides during a close encounter can warp disks, pull out streams of material, and induce waves that propagate through the interstellar medium. In the local group, Andromeda has not lived alone. It has long been surrounded by satellite galaxies, some of which are still intact, others already disrupted. The orbits of these satellites suggest that close passages have occurred repeatedly. Each passage would have exerted a tug, subtle but cumulative. Webb's observations hinted that such interactions may have influenced Andromeda's dust and gas more deeply than previously thought. Dust structures in the outer disk, faint but coherent, could reflect tidal stretching. Asymmetries between spiral arms might encode the direction and timing of past flybys. Ghost galaxies do not only leave stars behind, they bring gas and dust as well. When a smaller galaxy merges, its interstellar medium can be stripped and mixed into the host. Depending on conditions, this material may settle into the disk, fuel new star formation, or remain suspended in diffuse structures. If Andromeda accreted gas-rich companions in the past, their material could still influence present-day dust distribution. Differences in dust composition might reflect different origins. Regions where dust behaves differently could be places where external material was deposited and not fully homogenized. Chemical fingerprints support this idea. Studies of stellar metallicity in Andromeda have revealed variation across the disk and halo. Some stars appear more metal-poor or metal-rich than expected for their location. Such variation is consistent with accretion of stars formed in different environments. Webb's infrared data added another layer by linking dust behavior to these stellar populations. If dust in certain regions shares a chemical history with stars that originated elsewhere, it would behave differently under the same radiation field. This could help explain why some dust appears warmer or cooler than models predict. There is also the role of dark matter to consider. When a galaxy merges with or accretes another, it does not only gain stars and gas, it also absorbs dark matter. This can alter the gravitational potential in subtle ways, influencing orbital patterns and gas flows long after the visible merger signatures fade. Andromeda's dark matter halo is thought to be massive and complex, shaped by numerous past accretion events. Irregularities in that halo could influence the disk from below, creating non-uniform gravitational forces that affect where gas accumulates and how stars move. Webb's observations of uneven structure could reflect these deeper influences. Importantly, none of this implies that Andromeda's history was unusually violent. In fact, it may be quite typical. Most large galaxies grow through hierarchical assembly, gradually building mass by absorbing smaller systems. The difference is that Andromeda is close enough for us to see the details. For galaxies farther away, similar disturbances likely exist, but they blur together at lower resolution. Webb's observations of Andromeda serve as a reminder that even galaxies that appear orderly are products of long interaction histories. The idea of long-forgotten encounters also reframes how astronomers interpret present-day calm. A galaxy can look settled while still carrying the imprint of its past. The absence of obvious disruption does not imply isolation. It implies time. Time smooths sharp edges but does not erase everything. Some signatures persist, especially when embedded in components like dust and older stars that evolve slowly. Webb's infrared sensitivity is particularly well suited to detecting these lingering traces. For scientists, this realization encourages caution when labeling galaxies as undisturbed. It also motivates more detailed modeling that includes the cumulative effects of minor interactions, not just major mergers. These models are computationally demanding, but Webb's data provide the constraints needed to make them worthwhile. For a listener, especially one letting the mind drift, there is something quietly profound in this perspective. Andromeda's story is not one of sudden drama, but of gradual accumulation. Encounters remembered not as scars, but as textures. Ghosts not haunting, but quietly shaping. Collisions in this sense are not moments of destruction. They are moments of exchange. Matter moves, orbits change, new structures emerge. Over time, these exchanges become part of what the galaxy is. As the investigation continued, it became clear that understanding Andromeda's present required embracing its past in full, including events that left no obvious monuments. Webb's observations did not point to a single ghost galaxy or a single collision. They suggested many, layered one atop another, each contributing a small piece to the whole. This realization did not close the mystery, it deepened it. If Andromeda's structure reflects such a rich history, then interpreting Webb's findings means tracing not just what happened, but how different events overlap and interact over billions of years. When astronomers talk about galaxies growing old, they are not referring to a simple decline or a gradual fading into inactivity. Aging, in a galactic sense, is not a straight line. It is a process shaped by accumulation, by memory, and by the slow rearrangement of matter over immense spans of time. Webb's observations of Andromeda, especially the subtle irregularities and lingering signatures of past interactions, quietly reshaped how scientists think about this process. Not by overturning established ideas, but by adding depth to what it means for a galaxy to mature. For a long time, galactic aging was often described using broad categories. Young galaxies were active, chaotic, and rich in gas. Old galaxies were stable, orderly, and comparatively quiet. Spiral galaxies like Andromeda and the Milky Way occupied a comfortable middle ground. They were considered mature but not exhausted, still forming stars at a moderate pace, still maintaining clear structure. This framework remains broadly correct, but Webb's data suggested it is incomplete. Aging, it turns out, is not just about how much gas a galaxy has left, or how quickly it forms stars. It is also about how thoroughly a galaxy has mixed its past, how evenly it has redistributed the material it has acquired, and how deeply earlier events continue to influence present behaviour. One of the most important implications of Webb's observations is that galaxies may retain detailed memories far longer than previously assumed. In many models, time acts as a smoothing agent. Disturbances fade, structures relax, given enough rotation cycles, material spreads out and irregularities disappear. This assumption underlies much of how astronomers interpret present-day galaxy structure. Andromeda complicates that assumption. The fact that dust, stars, and heat still show uneven distributions linked to past interactions suggests that mixing is not always efficient or complete. Some features persist, not because they are actively maintained, but because the processes that erase them operate slowly or unevenly. This has significant consequences for how scientists interpret galactic maturity. A galaxy may look calm and symmetric on large scales while still being internally unsettled on smaller ones. Its apparent stability may mask ongoing rebalancing rather than final equilibrium. In this sense, growing old does not mean becoming simple. It can mean becoming layered. Each phase of activity, each interaction, adds another layer to the structure. Over time, these layers overlap, sometimes reinforcing one another, sometimes interfering. Webb's observations highlighted how dust plays a key role in this layering. Dust is often treated as a passive tracer, responding to radiation and gas flows, but dust also preserves history. Its distribution reflects where stars have formed, where energy has been deposited, and where material has been moved. In Andromeda, dust did not settle into a uniform pattern even after billions of years. Instead, it retained clumps, filaments, and temperature variations that pointed back to earlier events. This suggests that dust may be one of the most persistent record keepers in a galaxy, quietly encoding its past. The same applies to older stars. Once formed, stars can survive for billions of years, moving through the galaxy on orbits shaped by gravitational forces. If those orbits are altered by interactions, the stars carry that information forward indefinitely. Even when the original cause is long gone, the stellar distribution remains altered. Webb's data implied that some older stars in Andromeda occupy positions that make sense only when viewed in the context of past disturbances. Their presence challenges the idea that old stellar populations necessarily relax into smooth, featureless components over time. This forces a re-evaluation of how astronomers use stellar age as a proxy for stability. Old does not always mean settled. It can mean long-lived within a dynamic system that never fully stops evolving. Another implication concerns the role of minor interactions in galactic aging. Major mergers, where galaxies of comparable size collide, are dramatic and easy to recognize. They transform spirals into ellipticals, trigger intense starbursts, and erase orderly structure. These events are relatively rare. Minor mergers and flybys, by contrast, are common. A large galaxy like Andromeda may experience dozens or even hundreds over its lifetime. Each one adds a small perturbation. Individually, they may seem insignificant. Collectively, they shape the galaxy's long-term evolution. Webb's observation suggested that these small interactions matter more than previously thought, especially for how galaxies age internally. Rather than pushing a galaxy toward a simple, quiescent end state, repeated minor encounters may keep it subtly stirred. They redistribute material, introduce asymmetries, and prevent complete relaxation. This challenges the notion that aging leads inevitably to uniformity. Instead, it suggests that for spiral galaxies, aging may involve maintaining structure while accumulating complexity. Star formation history also takes on a new nuance. Traditionally, astronomers track aging by measuring how star formation rates change over time. When star formation declines, a galaxy is considered older or more evolved. Andromeda does have a relatively low current star formation rate compared to more active spirals. Yet Webb's data showed that even with modest star formation, energy continues to circulate through the galaxy in uneven ways. Dust heating does not shut off cleanly. Older stars continue to influence their surroundings. Residual effects from past star formation persist. This implies that the transition from active to passive is not abrupt. It is gradual and patchy. Some regions may effectively retire, while others remain influenced by long-lived processes. The idea of galactic retirement, where star formation simply winds down and the galaxy settles into quiet uniformity, may be too simplistic. Webb's observations encourage a view where galaxies age unevenly, with different regions reaching different evolutionary states at different times. Another important implication involves how astronomers classify galaxies. Many classification schemes rely on global properties: overall color, average star formation rate, total gas content. These metrics are useful, but they can obscure internal diversity. Andromeda's global properties place it firmly among mature spiral galaxies. Webb's data revealed that internally it behaves more like a patchwork of environments at different evolutionary stages. Some regions resemble older, more passive systems. Others show signs of relatively recent disturbance or lingering activity. This internal diversity complicates comparisons between galaxies. Two galaxies with similar global properties may have very different internal histories. Webb's observations suggest that understanding galactic aging requires looking beyond averages. This has implications for studies of distant galaxies as well. For galaxies billions of light-years away, astronomers often rely on integrated light measurements. Webb itself will observe many such systems. Andromeda serves as a reminder that integrated properties can hide significant internal variation. If distant galaxies share similar complexity, then interpretations based solely on global metrics may miss important aspects of their evolution. Andromeda becomes a kind of calibration tool, showing what complexity looks like when it can be resolved. There is also an implication for how astronomers model galactic evolution. Many simulations aim to reproduce average trends across populations of galaxies. While successful in broad terms, these models often struggle to reproduce fine-scale structure and long-lived irregularities. Webb's observations suggest that incorporating detailed histories of minor interactions, dust physics, and stellar migration is essential for realistic modelling. This is computationally demanding, but it may be necessary to capture how galaxies actually age. Another subtle implication concerns the relationship between appearance and history. Andromeda looks calm because its large-scale structure is stabilized, but calmness does not imply inactivity. It implies balance. That balance may be dynamic rather than static. Energy continues to move, material continues to shift, past events continue to influence present conditions. Aging, in this view, is not about stopping, but about changing how change occurs. For spiral galaxies, aging may mean transitioning from dramatic large-scale transformations to quieter, internal adjustments. The galaxy does not stop evolving, it evolves differently. This perspective also affects how astronomers think about the future of galaxies. Andromeda is on a slow collision course with the Milky Way. That future merger will dramatically reshape both galaxies. But before that happens, both will continue to age in this subtle, layered way. Understanding Andromeda's current state helps astronomers model what the Milky Way may look like at a similar stage, and how both might respond to future interactions. There is a philosophical dimension to this as well. In human terms, aging is often associated with loss. In galaxies, aging appears to be associated with accumulation. More stars, more interactions, more history layered into structure. Webb's observations invite a shift away from viewing galactic aging as decline and toward viewing it as narrative. Each galaxy carries a story written in matter and motion. The older it gets, the longer that story becomes. For someone listening quietly, perhaps letting these ideas drift by, there is something calming in this reframing. The universe does not rush toward an end state. It accumulates experience. Andromeda's irregularities are not flaws. They are chapters written slowly, preserved not in words but in dust, stars, and heat. Webb's contribution was to make those chapters easier to read. As the implications of this view settled in, attention naturally turned toward the most personal comparison available. If Andromeda's aging is complex and layered, then the Milky Way's aging must be as well. The two galaxies share similar mass, structure, and environment. They have likely experienced similar histories, even if the details differ. Understanding what Webb revealed about Andromeda therefore extends beyond a single galaxy. It informs how astronomers think about spiral galaxies in general, including our own. It suggests that when we look at the Milky Way and see apparent calm, we may also be looking at a system rich with quiet memory. When astronomers talk about Andromeda, there is always an unspoken second subject in the room, the Milky Way. No matter how distant or abstract the discussion may seem, it inevitably circles back to the galaxy we inhabit. Andromeda's mystery matters not simply because it is interesting on its own, but because it is the closest large mirror we have. It offers a view of what a spiral galaxy like ours looks like from the outside, carrying clues that we cannot easily extract from within the Milky Way itself. From our position inside the Milky Way's disk, our perspective is deeply limited. Dust obscures vast regions of the galaxy. Spiral arms overlap along lines of sight. Distances are difficult to measure precisely. Even basic questions about the Milky Way's overall structure have taken decades to resolve and remain topics of active research. In contrast, Andromeda lies before us almost in full, its disk, bulge, and halo visible as a coherent system. Because of this, Andromeda has long served as a reference point. It is not identical to the Milky Way, but it is similar enough in mass, size, and structure to make comparisons meaningful. When astronomers test models of spiral galaxy formation and evolution, Andromeda is often one of the first benchmarks. If a model cannot reproduce Andromeda, it is unlikely to describe the Milky Way accurately. This is why Webb's observations carry such weight. The subtle inconsistencies revealed in Andromeda are not isolated curiosities. They raise questions that apply directly to our own galaxy. If Andromeda, a system we believed we understood reasonably well, turns out to be more complex internally than expected, then the same is almost certainly true for the Milky Way. One of the most important parallels involves galactic history. Like Andromeda, the Milky Way has not lived in isolation. It is surrounded by satellite galaxies, some intact, others already in the process of being torn apart. Stellar streams arc through our halo, clear evidence of past mergers. The Sagittarius dwarf galaxy, for example, is currently being absorbed, its stars stretched into a vast loop around the Milky Way. These events are ongoing reminders that the Milky Way's structure is shaped by interaction. Yet when astronomers describe the Milky Way's disk, it is often portrayed as relatively undisturbed in recent times. Major mergers are thought to lie far in the past. The disk appears thin and coherent. Spiral arms are well defined. On the surface, this suggests stability. Webb's observations of Andromeda suggest caution with such interpretations. If Andromeda's disk can carry subtle, long-lived imprints of past interactions while appearing calm overall, then the Milky Way's disk may do the same. Features we currently attribute to internal processes alone may, in fact, be influenced by ancient encounters whose signatures are difficult to isolate from within. Dust provides a striking example. In the Milky Way, dust clouds shape our view of the galaxy. They obscure starlight, define star-forming regions, and structure the interstellar medium. But because we are embedded within this dust, mapping its full three-dimensional distribution is extremely challenging. Webb's view of Andromeda shows how dust can retain irregular structure for billions of years, influenced by interactions, stellar populations, and dynamics. If similar processes operate in the Milky Way, then our own dust distribution may encode a complex history that we have only partially decoded. The same applies to dust heating. Webb revealed that older stars in Andromeda may contribute more significantly to dust heating than previously assumed. In the Milky Way, infrared emission is often used to trace star formation, under the assumption that young stars dominate dust heating. If older stars play a larger role than models account for, this could affect how astronomers interpret infrared surveys of our own galaxy. Regions assumed to be actively forming stars might instead be influenced by dense populations of older stars. Conversely, some star-forming regions might appear cooler than expected due to local conditions. This has practical consequences. Much of what we know about star formation rates, both in the Milky Way and in other galaxies, relies on calibrations derived from infrared emission. If those calibrations are incomplete, then estimates of star formation history may need revision. Another parallel lies in stellar populations. Webb's observations suggested that older stars in Andromeda sometimes occupy unexpected locations, possibly as a result of past mergers or migration. In the Milky Way, there is growing evidence that stellar migration plays a significant role in shaping the disk. Stars can move far from their birthplaces due to interactions with spiral arms, bars, and satellite galaxies. As a result, the present-day distribution of stars does not necessarily reflect where they formed. Webb's findings reinforce the idea that interpreting stellar populations requires accounting for long-term movement and external influence. This is especially relevant for studies that use stellar age and composition to reconstruct the Milky Way's history. Large surveys, such as those conducted by Gaia and other missions, have revealed complex structures in the Milky Way's stellar distribution. Webb's view of Andromeda suggests that similar complexity is not exceptional, but expected. There is also the matter of symmetry. From our position within the Milky Way, assessing large-scale asymmetry is difficult. Webb's observations of Andromeda revealed subtle but persistent imbalances between different regions of the disk. If similar imbalances exist in the Milky Way, they may be difficult to detect from within, yet still influence gas flows, star formation, and disk stability. Understanding Andromeda helps astronomers recognize what kinds of asymmetry are normal, what might indicate past interaction, and what might arise from internal dynamics alone. It provides a template for interpreting features in our own galaxy that might otherwise be misattributed. Perhaps the most compelling reason Andromeda's mystery matters is the future it shares with the Milky Way. The two galaxies are gravitationally bound and moving toward each other. In roughly 4 billion years, they are expected to merge. This future collision is often described as a dramatic event, but it will be shaped by the internal states of both galaxies at the time it occurs. Their gas content, stellar distributions, and dark matter halos will all influence how the merger unfolds. Understanding Andromeda's current structure including its subtle irregularities and layered history, helps astronomers model this future encounter more realistically. If Andromeda carries the imprint of many minor mergers, those imprints will affect how it responds to the Milky Way's gravitational pull. Likewise, the Milky Way's own history will shape the merger. If our galaxy also carries hidden complexity, the resulting system will reflect the combined memories of both. Webb's observations of Andromeda offer a preview of how long-lived such memories can be. There's also a broader methodological lesson. Astronomy often relies on studying external galaxies to understand our own, but this approach assumes that those external galaxies are simpler to interpret. Webb's findings challenge that assumption. If even Andromeda, our nearest large neighbour, resists tidy interpretation, then the Milky Way may be even more complex than we realise. This does not undermine the comparative approach. It enriches it by reminding astronomers to account for hidden structure and layered history. Another implication concerns how astronomers think about the local group as a whole. The Milky Way and Andromeda are the dominant members, but they are surrounded by dozens of smaller galaxies. Their interactions shape the environment for all members of the group. Webb's observations suggest that Andromeda has been shaped significantly by its satellites. The Milky Way likely has been as well. Understanding one system helps illuminate the dynamics of the entire group, including how material moves, how galaxies grow, and how interactions cascade over time. From a more human perspective, Andromeda's mystery matters because it reframes our sense of place. When we look at Andromeda in the night sky, we're not just seeing another galaxy, we're seeing a future counterpart to our own, a system that shares our environment, our fate, and perhaps many aspects of our history. Webb's observations remind us that this future counterpart is not simple or static. It is a living system shaped by countless interactions carrying memory in its structure. The Milky Way, by extension, is likely the same. For someone listening quietly, perhaps late at night, this connection adds intimacy to the vastness. The universe is immense, but patterns repeat. The processes shaping Andromeda are shaping the Milky Way. The questions raised by Webb are not distant curiosities. They're questions about home. This perspective also influences how astronomers prioritize future observations. If Andromeda can reveal hidden complexity with Webb, then detailed infrared studies of the Milky Way's outskirts, halo, and dust structures become even more important. Webb may not be able to map the Milky Way in the same way due to our internal vantage point, but it can still provide crucial pieces. Combining Webb's data with other missions allows astronomers to cross-check interpretations. Features seen externally in Andromeda can be sought internally in the Milky Way, even if they appear differently. This comparative approach becomes more powerful when informed by the level of complexity Webb has revealed. There is also a humbling aspect to this realization. For many years, astronomers believed they had a fairly complete picture of how spiral galaxies like the Milky Way evolve. Webb's observations of Andromeda suggest that picture is still being refined. The basics are sound, but the details matter, and those details accumulate slowly, through careful observation and comparison. They do not arrive as revelations, but as quiet adjustments to understanding. Andromeda's mystery matters because it keeps the Milky Way story open. It suggests that there is still much to learn about how our galaxy came to be the way it is, and how it continues to change. It reminds us that familiarity does not equal simplicity. There is a particular kind of lesson that emerges not from shock, but from quiet adjustment. It does not arrive with headlines or sudden reversals. Instead, it settles slowly, changing how we hold ideas we thought were already secure. That is the kind of lesson the universe offers when it surprises us gently, as it has through Webb's view of Andromeda. Nothing about Andromeda collapsed under scrutiny. Its spiral arms did not dissolve. Its stars did not scatter. The physical laws governing it did not fail. And yet what Webb revealed was enough to soften certainty, enough to remind scientists that understanding is provisional, layered, and always subject to refinement. One of the most important things we learn in moments like this is that precision changes responsibility. When tools improve, the obligation to think carefully increases. Webb did not merely add detail to old pictures, it changed the scale at which questions must be asked. Features once smoothed into averages became distinct. Relationships once assumed to be tight became conditional. This is not a failure of earlier science. It is how science is meant to work. Models are built for the data available at the time. They succeed by capturing dominant behavior. When better data arrives, those models are tested not at their strongest points, but at their edges. Andromeda lived for decades at the center of a well-supported framework. It was the nearby spiral that behaved, the reference galaxy, the calm neighbor. Webb did not overturn that role, but it complicated it. Calmness, it turns out, can coexist with imbalance. Order can persist alongside irregularity. Stability does not require uniformity. That realization carries weight beyond a single galaxy. It changes how astronomers interpret patterns everywhere. When a distant galaxy appears smooth in low-resolution data, it may not be simple. It may be layered in ways we cannot yet see. When star formation indicators disagree, the discrepancy may not signal error, but history. One lesson is that galaxies do not forget easily. Time does not erase everything. It redistributes, stretches, blends, but some imprints remain. Dust remembers where energy flowed. Stars remember where gravity nudged them. Gas remembers where it was compressed or pulled apart. These memories persist not as narratives, but as structure. Webb's observations suggest that memory can be subtle. Not a single dramatic scar, but many small deviations from expectation. Each deviation modest, together meaningful. Another lesson concerns patience. The temptation when encountering unexpected data is to resolve it quickly, to find a single explanation that restores simplicity. But the universe rarely offers such closure. More often, it invites slower synthesis, multiple processes overlapping, causes that reinforce or counteract each other. In Andromeda's case, no single factor explains everything. Minor mergers matter, but so does stellar migration. Dust physics matters, but so does geometry. Heating sources overlap. Timing matters. Perspective matters. Learning to live with that complexity is part of scientific maturity. It requires letting go of the idea that understanding must feel tidy. Instead, understanding can feel textured, coherent without being neat. There is also a lesson about humility. Webb did not reveal that astronomers were wrong in any absolute sense. It revealed that they were incomplete. That distinction matters. Incompleteness is not a flaw. It is an invitation. Every generation of instruments reveals what the previous generation could not. Hubble reshaped our sense of scale. Spitzer illuminated dust and hidden star formation. Webb now connects those insights with resolution that forces reconsideration. None of these steps invalidates the last. They extend it. Andromeda's mystery reminds us that proximity does not guarantee mastery. We can observe something for centuries and still find new layers when we learn how to look differently. Familiarity breeds confidence, but confidence must remain flexible. There is something instructive in how understated this surprise has been. No alarms, no rewriting of textbooks overnight, just careful notes accumulating, questions adjusting, conversations deepening. That is how progress usually looks from the inside. Dramatic moments are rare. Most change happens quietly through recalibration. Another lesson lies in comparison. Andromeda matters because it stands beside the Milky Way, not above it. It is similar enough to teach us, different enough to caution us. When Andromeda behaves in ways that challenge assumptions, those challenges echo inward. If Andromeda carries layered memory, so does the Milky Way. If Andromeda's dust and stars reflect long-forgotten encounters, ours likely do as well. The difference is perspective. From the outside, complexity is revealed through structure. From the inside, it must be inferred through motion, chemistry, and indirect mapping. This means that some puzzles in Milky Way astronomy may not be solvable through better data alone. They may require accepting that some signals reflect accumulated history rather than ongoing processes. Webb's view of Andromeda strengthens that interpretation. Another lesson is about expectation itself. Expectations are necessary. Without them, data has no meaning. But expectations must be held lightly. They should guide attention, not constrain it. In Andromeda's case, expectations were strong because the galaxy was well studied. That strength made deviations easier to notice. In less familiar systems, similar deviations might go unrecognized or be dismissed as noise. This suggests that surprises are not always where we look least. Sometimes they are where we look most, precisely because we think we already understand what we are seeing. There is also a broader lesson about how the universe communicates. It does not announce complexity. It reveals it when we develop the sensitivity to detect it. Webb did not create Andromeda's irregularities. It revealed them. That distinction matters when thinking about discovery. Discovery is not always about finding something new in the universe. It is often about finding a new relationship between things we already knew. Dust and stars were always there. Heat was always moving. Webb made their relationships legible at a finer scale. From a human perspective, there is something reassuring in this. The universe is not capricious. It does not change suddenly to confound us. It remains consistent while our understanding evolves. This kind of surprise does not destabilize. It deepens. It encourages curiosity without urgency. It rewards attention rather than reaction. For those listening in quiet moments, perhaps late at night, this has a particular resonance. The universe becomes less like a puzzle to be solved and more like a landscape to be explored slowly. Andromeda does not demand explanation all at once. It allows time. It allows revision. It allows uncertainty to coexist with knowledge. There is also a lesson about scale. On human timescales, galaxies seem static. On cosmic timescales, they are dynamic. Webb's observations remind us that even when change is slow, its effects accumulate. A minor merger every few 100 million years may seem inconsequential. Over billions of years, it shapes identity. Aging, in this sense, is not erosion. It is accumulation. This reframing alters how astronomers think about galactic life cycles. The end state is not uniform stillness. It is layered balance. Motion continues, energy flows, memory persists. Another subtle lesson is about interpretation itself. Data does not speak alone. It requires context, comparison, and restraint. Webb's images were beautiful, but beauty did not equal understanding. Understanding emerged only after careful correlation with other data sets, models, and histories. This is important because images often dominate public perception of astronomy. They suggest immediacy and clarity. The reality is slower and more deliberate. Webb's Andromeda images did not provide answers. They provided better questions. Questions like how long disturbances last, how efficiently galaxies mix material, how internal and external processes interact, how much history can remain visible without obvious structure. These questions do not point toward a single conclusion. They point toward continued observation and modelling, toward refinement rather than resolution. And that brings us to one of the quietest lessons of all. Science does not always aim for closure. Sometimes its purpose is to keep understanding open, flexible, and responsive to new information. Andromeda's mystery does not end with Webb. It begins a new phase. Future observations will refine interpretations. New instruments will add context. Models will adjust again. Even Webb itself has not finished looking. What we have discussed reflects early analyses, not final consensus. As more data accumulates, some anomalies may resolve, others may deepen. This ongoing process is not a flaw. It is the rhythm of inquiry. For someone easing toward rest, there is something fitting in that rhythm. No final answers, no sharp endings, just a steady unfolding. The universe does not rush to be understood. It invites us to keep pace with it, slowly. Andromeda will continue to shine faintly in the night sky, unchanged to the eye. Webb will continue to refine how we interpret its light. The Milky Way will continue its own quiet evolution, carrying memories we have not yet learned how to read. What we learn when the universe surprises us is not that it is unpredictable, but that it is deeper than our current descriptions. That understanding grows not by replacing what came before, but by expanding it. That lesson extends beyond astronomy. It suggests a way of approaching complexity without frustration, of accepting that clarity can coexist with uncertainty. As this exploration gently settles, there is no need to conclude anything. Andromeda remains where it has always been. Webb continues its work. Questions remain open. And in that openness, there is room for rest, for curiosity without demand, and for the quiet reassurance that the universe reveals itself at a pace that does not require us to hurry.